get my slides up. Thank you. So Cocoon is the first IFC approach, information flow control approach, for an off-the-shelf language that does not require modifying the language or compiler. So let's start with a motivating example. We have two users, Alice and Bob. Alice and Bob would like to find how many possible times they can meet, how their calendars line up so they can actually meet with each other. They would like to send their calendars to a piece of code, denoted by the orange circle here, that finds the shared availability and returns the number of possible meeting times. However, what Alice and Bob do not want is for this code to send back, sure, the number of possible meeting times, but also Bob's entire calendar to Alice, or for that matter, to anyone else. Bob's calendar should only go to Bob, and Alice's calendar should only go to Alice. We don't want this. So one approach that can be used for this is access control. Access control could block off the flow of information and say, okay, well, Alice and Bob can't send their calendars to this code that could be doing bad things. However, in that case, then Alice and Bob can't find what days they can meet on, how many days they can meet on. They can't do what they want. It limits things too strictly. An alternative is access control could say, okay, fine, it can go ahead and pass through, and then great, Alice and Bob can send their calendars through, the code can go ahead and find the availability and send it back. But then we once again have the threat model. We have Bob's calendar can be sent through. Access control doesn't discriminate between different types of information. It just blocks off flows completely or allows them through completely. So access control can't solve this problem. Access control can't let us do what we want. An alternative is information flow control, or IFC for short. In information flow control, each piece of data is labeled with a specific level of secrecy. So in this case, you can see Alice's calendar is marked seek A. In other words, it is marked as secret to Alice. Only Alice should be able to read her calendar. Similarly, Bob's calendar is marked seek B. It's secret to Bob. Only Bob should be able to read his calendar. In this model, in the way IFC would tackle this problem, the code goes ahead and computes the availability. It's allowed to read both seek A and seek B. And then it spits out the number of possible meeting times marked with both Alice's and Bob's secrecy labels. Notably, because seek A means only readable by Alice and seek B means only readable by Bob, seek A and B means readable by no one. No one is allowed to read it. It is secret to everyone, which means no one can read it. So in the IFC approach, this secretly marked number of possible meeting times is sent out to another piece of code denoted by the green circle that declassifies it, lowers the secrecy level, and returns the number of possible meeting times marked with Alice's secrecy to Alice and marked with Bob's secrecy to Bob. So in this case, exactly the data that we want to get across is coming across. The calendars are going where they need to, the number of possible meeting times is going where they need to, everything is functioning. So what if the bad thing happens again? So the availability finder sends across Bob's calendar. Bob's calendar is still marked with secrecy B because you can't just take off secrecy labels without explicitly declassifying. It gets sent to the declassifier, and the declassifier looks at this and says, no, this doesn't match what's supposed to happen. No, we're not declassifying this, and the threat stops there. So information flow control lets us do what we want. It lets us tackle this problem. It lets Bob and Alice keep their calendars private, but share their availabilities. So some prior work enforcing IFC. The first type that I'm going to discuss is interprocedural analysis. Interprocedural analysis is generally done after code has been written. It's generally done analyzing already written and produced code. It walks through it and analyzes it to see how does the information flow, where does it go, how does it move. The problem with interprocedural analysis is that it's non-compositional. It doesn't really preserve context very well. It tends to forget or not keep track of how information is going outside of the specific context being analyzed. With multiple different contexts, this means that it kind of has to assume the worst case scenario, and things get marked with higher and higher secrecy labels. And what tends to happen is everything gets marked as super high secrecy, even if it doesn't need to be. This is obviously bad. This isn't what we want. This isn't the best approach. An alternative is dynamic analysis. Dynamic analysis is performed at runtime. This lets it go ahead and keep track of the context. It lets it pass data back and forth between different contexts and keep track of exactly what's going on. Great. The problem is it's at runtime. This means high performance cost. This, again, is a problem. We don't want to slow down our CPUs. We don't want to add overhead to perform IFC. The final approach that I'm going to discuss here is type-based analysis. Type-based analysis is similar to dynamic analysis in that it often involves modifying the code itself, modifying the code to explicitly handle information flow control. It keeps track of context, lets the program keep track of where the context is, where the data is going, where it's come from, what its labels exactly are. The problem with type-based analysis is that it requires modifying the language or compiler with one exception, Cocoon, which is what I'm talking about today. Cocoon, again, is the first IFC approach for an off-the-shelf language for Rust that doesn't require modifying the language or compiler. Cocoon is implemented as a library in Rust, and programs that use Cocoon import the library and then modify their code or write their code in the first place so that it uses that library. So let's back up and talk about that motivating example again. To remind you, we have Alice and Bob want to send their calendars to a piece of code, find the shared availability, and tell them how many days they can meet on. How would we write this example with Cocoon? Well, to start with, we have Alice's calendar and Bob's calendar, both represented by hash maps, with an example entry in the hash map up to the right there. So you have Monday mapping to a secret value, secret true, or to secret false for Bob in this case. Secrets are denoted by, or secrets are handled by, they are wrapper types around a piece of data. So in this case, a secret holds a Boolean and a static type. You can see it there as lat A or lat B. These static types represent the labels. So lat A in this case represents Alice's secrecy label. Lat B represents Bob's secrecy label. These are static types. It marks the data as secret to that level and preserves secrecy. So, again, in this example, we need to initialize a counter. The goal of this is to count how many days can we meet on. So we need to initialize a counter. This counter needs to be able to interact with secret data. So it needs to have a label of AB. It needs to be as secret as Alice and as secret as Bob's data. So we create it using a struct or a type of secure code region called a secret block. A secret block has an associated secret label, in this case AB. And inside of a secret block is where you can interact with secret data. In this case, we're creating a new secret by calling wrap secret. There are a few functions that can only be called inside of secure regions, as in they will not work if called outside of secure regions. Secure regions specifically handle the code in such a way that it gets turned into an appropriate call and can be used. If you attempted to call wrap secret outside of a secure block, you would get a compiler error, nothing would happen. So we've created our counter. Now we need to iterate through the days in Alice and Bob's calendar. So we iterate through Alice's calendar and we use another secret block. Again, it's interacting with both Alice and Bob, so it has label AB. We need to perform a check. We essentially need to check, is Alice available, is Bob available? We have Alice's availability here, although it's secret, so we use unwrap secret. Is Alice available? Okay. If that's the case, we then need to query Bob's calendar using hashmap get and option unwrap. This returns a secret of Bob's availability, and we use unwrap again to check if Bob is available. Great. Then, if they are both available, we need to increment our counter. So we use unwrap secret mute ref. This just means that we are able to mutate the variable that's getting unwrapped, so we pass in the counter, and we increment it by 1. This loop continues, passes through all the days, and at the end, we want to return how many days there are, so we need to explicitly declassify. Declassification is the one area that needs to be audited in this code for us to verify that it works properly. One of the major benefits of information flow control is done properly, it greatly reduces the trusted code base. With this code written in Cocoon, none of this code needs to be audited, none of it needs to be trusted, all of it will guarantee secrecy, except this last line where you are explicitly declassifying. So you need to make sure, am I actually declassifying what I'm supposed to? But beyond this, all of this can be trusted. So let's talk about some of the threats that we had to handle, and all of these are handled and discussed in greater depth in the paper, so I'd recommend you take a look at that for any further curiosity you have, but I'll run through a few of them real quickly. So first of all, what if we try to do this? What if we initialize a variable outside of the secret block and it's not secret, and then we try to increment it inside? Well, we don't want that. That is just explicitly passing secret data outside. This is prevented via using Rust's type system and procedural macros system. We can use some of the particular features of Rust to disallow this behavior. And again, more details are in the paper. Second, we want to disallow function calls that could have side effects. In this case, we don't want it to write to a file day available every time a day is available. This is, again, explicitly violating information flow control. Again, we prevent this using types and types and procedural macros. In this case, the result is that no functions except for ones that we explicitly know are safe can be called inside of secret blocks, as in the macros will not compile and you will not be able to write code that does this. Finally, there is a particular set of side effects inside of Rust that is invisible. So what if we made our counter implement a type or implement drop specifically, so it has a custom destructor? When it gets destroyed, I didn't include it here for space, but say when it gets destroyed, any piece of code could be inserted here. We could have a print line, we could have it do whatever we wanted. We could have it print out everything that's been done. Again, obviously bad. And again, handled via procedural macros and type specifications. Rust is pretty cool, in case you didn't know. Lets us do some neat stuff. So let's move on to the case studies for Cocoon. So with these case studies, our goals were to test the usability of Cocoon, to test that Cocoon is incrementally deployable, as in you don't need to rewrite an entire several thousand line program if you need to keep one thing secret in one place over 50 lines. You can just alter those. Finally, we wanted to test the performance overhead. Our main claim to improvement over dynamic analysis is that we don't have performance overhead, so let's make sure that's true. So we implemented Cocoon as a Rust library, took real Rust programs, added Cocoon as a library, and then modified those programs to use Cocoon. First is Battleship. Battleship is to test incremental deployment. This is a game where two players are competing against each other. Each player has secret information and is trying to guess the other one's secret information. So we want to protect the secret data, but allow the guesses to go through. So we need two-way flow of data, but two-way flow of specific data. This is also based on some prior work that was done in the GIF paper on information flow control a while ago. So we built this, it works, and there was no runtime overhead. Next is Spotify TUI. This is a real-world program. This is a text-based Spotify interface, so a way to interact with Spotify from your data terminal on your computer. We wanted to protect the user authentication secret, something equivalent roughly to the password that lets Spotify know you are you. We did this, it works, and there was no runtime overhead. And finally is Servo. Servo is another real-world program. It is a web browser and rendering engine, very popular Rust program. At the time of the paper's writing, I believe it was top 10 most starred project on GitHub written in Rust. As of 2 days ago, I think it was 29th, so it's fallen a little bit, but still very popular. And for this one, we wanted to protect HTTP responses from cross-origin readers. In other words, if you're entering your data onto a web form and there's an ad on that web form, that ad shouldn't be able to read your data. So we did this, it works, and again, there was no runtime overhead. So in conclusion, Cocoon is the first IFC approach for an off-the-shelf language that does not require modifying the language or compiler. Thank you.
Hi, thanks for the talk. You carefully avoided having to modify the language or compiler. What I'm wondering about is, suppose you relax that restriction. There was a bunch of sort of explicit code in there dealing with secrets. And obviously, or presumably, you want to explicitly declassify. But the other code, I wonder whether you maybe want to do that implicitly, and if you've thought about what that would look like.
I'm sorry, I think I missed the last sentence. You were saying, I wonder if, and then I missed the rest of it.
I wonder if the operations involved in secrets, other than declassification, might be better if done implicitly, rather than explicitly via function calls, macros.
It could. Can you please repeat the question? Certainly. Let me, please tell me if I'm getting this wrong at all, but I believe the question was, if we relax the restriction on we don't want to modify the language or compiler, would it be better to try to make operations on secrets, non-declassify operations like adding 2 secrets or subtracting 2 secrets or something like this, make those implicit, so don't require actually adding all that extra code, the secure blocks? I could see a case where that could be significantly easier to write at the very least. It would require almost certainly modifying the compiler. But yes, I could see where that would ease programmer burden. The main con would just be it would require modifying the compiler, which we are trying to avoid doing because modifying the compiler significantly impairs how easy it is to adopt for your average programmer.
Thank you.
Certainly.
Thank you for the talk. It's really cool. Just one small question. Do you support async code, which would put all the variables on the stack?
I do not believe we do.
Okay.
I'm not willing to swear to that. I'd have to go check exactly, but I do not believe we support async code.
And would you recommend that people compile their code with abort on panic?
It could depend on the goal of the code being compiled. Probably for release code, you want to compile with abort panic on. Actually, it shouldn't matter. The way Cocoon handles panics is Cocoon actually instantiates a new panic handler for every secure block. So panics from inside secure blocks get caught and handled in a custom Cocoon way that doesn't cause problems.
That's cool. Thank you.
Certainly.
Hello, thanks for the talk. So did you find any real-world programs where you could not use Cocoon because you are disallowing some features, right, because of the side effects and so on?
I don't believe that we came across many programs that we couldn't use Cocoon on for that reason, for the things that we're disallowing. We did have a number of programs where it was tricky to use Cocoon at times just because not every program has an obvious policy, has an obvious thing that's secret that we want to preserve. But no, we didn't really come across any programs where the restrictions imposed by Cocoon caused problems.
Okay, thank you.
Certainly.
So our second speaker comes from Cornell, and Eric will present work about computing precise control interface specifications.
Can you hear me? Good? Okay. Sorry, I've lost my pointer. Okay, hi. I'm Eric. Thanks for the introduction. I'm a PhD student at Cornell. I'm starting my postdoc with Ishul Diller next week, as well as with Aditya Kella. So, okay, I'm going to talk to you about computing precise control interface specifications. And you might imagine my glee when I heard Todd's talk this morning, because we are going to be talking about networking programs. But first, let's start with the unknown. Specifically, I want to understand how we can reason about programs with unknown code. Let's start with a verification myth, a broad, general misconception that we're all guilty of. When we embark on the project of verifying a program P, that is, that it satisfies some specification phi, we assume that we have the entire text of the program P, the entire AST, so that we can use our syntactic verification technologies like OR logic or weakest preconditions. But for real code written by real engineers, software, the source code is often incomplete. That is, large portions of code are often unknown to the programmer, hidden behind libraries, module boundaries, as system calls. And so really, when we're doing this verification, our program is dependent on a set of unknown functions. So how do we ensure that our program P over these functions F satisfies our spec? Let's look at some example Pythonic pseudocode. We'll import two functions, foo and bar, from some module called unknown, whose implementation is inaccessible. In this code, parameterized on x, we'll run foo to get y, and then run bar to get z, and assert that the bitwise OR of y and z is not equal to 0. And we want this assertion to never fail. To verify this code, we're tempted to be pessimistic and sort of say, does this hold for all implementations of foo and bar? And of course the answer is no, because we can just set both of them to zeros, and then their bitwise OR is going to be 0. Okay. We could take the optimistic approach, the other extreme, and say, okay, maybe this is a very good engineer who's implemented foo and bar, and they've predicted our needs precisely. And they've managed to find some implementation, if it exists, that satisfies the spec. But this is also sort of trivially satisfiable. And all we've learned here is really that on one extreme, there's an implementation that satisfies the specification. And on the other extreme, there's an implementation that violates the specification. And I don't know, maybe this is interesting to you, but I'm more interested in the question of which implementations of foo and bar satisfy our specification, satisfy this assert statement. Okay, we're not the first to ask this question, so let's look at some related work. Related work has computed interface specifications that are independent. That is, they're sets of single function conjuncts. This manifests as a conjunction of single function first order logic sentences where each conjunct constrains just one function from the interface. And the idea is that each function in a module should have its own specification that's distinct from the other specifications, from the other functions in that module. This Popple 16 paper called Maximal Specification Synthesis computes specs that are both safe and maximal, where maximal here means that no conjunct can be safely weakened. If we were to run our tool this tool on this example, the interface spec we would infer simply enforces that foo and bar can never produce 0 at the same time. And as we saw in our previous example where one produced all f's and one produced all zeros, that's sort of overly restrictive for this example. On the flip side, we could err on the other extreme and follow this approach using necessary preconditions from SIGCOMM 2020. And a necessary precondition is this Cousseau and Cousseau idea from VMCI 13, where you try to eliminate no good runs from the program. And in this case, there's actually no way to eliminate no good runs, eliminate also satisfy our syntactic requirement. So we just infer true here. Or this tool just infers true. And of course, this is not safe. This is wildly permissive and also not going to give us any good information. So it seems that as far as related work goes, engineers have to make a trade-off between the permissiveness of their specifications and their safety. We aim to have the best of both worlds. So for a program with functions f that want to satisfy our specification, our goal is to compute an interface specification for these f's that is safe, of course, it prevents any bugs that might occur, and it's also maximally permissive. And we're going to unify both of these concepts into a notion called precise. which just means that the set of functions f satisfies the interface specification if and only if using that implementation in the program p satisfies phi. We're also going to have this notion of efficiency of specifications, but we'll discuss that in more detail later on. So let's see what a precise spec looks like for our example program. In this example, we can easily compute it by starting with the assertion and working backwards, substituting in our function invocations. And hopefully that's convinced you that this specification is actually equivalent to the program that we had before. This spec improves on previous work because it is safe and maximally permissive, and it's also weakest, which you can approximate for now as just meaning that there's no unnecessary variables, there's no unnecessary stuff going on here. So what can we do with the spec? Well, we usually think of specs as being these human-written objects that we can use for things like documentation or manual verification. But computed specs are often not human-readable. They're often comprised with lots of machine gobbledygook that's hard for humans to parse. But that makes them also great for automated verification, because computers can actually understand all of their own gobbledygook. So in this paper, we'll focus on the specific use case of computer networking. We heard from Todd earlier about how verification in the networking domain is flummoxed by unknown, by these dynamically configurable pieces of information. He focused on verifying the control plane protocols like BGP or OSPF, but in general, the control plane can be some sort of bespoke, say, software-defined networking piece of software. And here we're going to peel back one layer of abstraction, and rather than focus on these protocol-level bugs that Todd was talking about, we're going to focus on program-level bugs in the data plane pipeline. So if you were at the keynote, you heard talk about these forwarding tables, which are computed dynamically at runtime to correspond to changing network conditions. And these serve as the unknown functions that are plugged into these data plane pipelines. However, as is common in systems design, the set of tables that we can syntactically express is much greater, it's much more permissive than the set of tables that the data plane pipeline can actually handle. And so if we can precisely capture the permitted configurations using an interface specification, then we can improve the robustness of the network. For example, by producing a runtime monitor that rejects buggy configurations, or using them as an input to a tool like Batfish. So this is where our work, Capiche, fits in. Capiche computes control interface specifications, CI specs, that are precise, which means they're both safe and maximally permissive, and also efficient to check. Let's jump into how we do this. Our first step is to define an abstract model of pipeline programs. And for expositional purposes, we'll jump into the middle of the pipeline, where we use Dijkstra's guarded command logic, a modern version of it, over a set of uninterpreted functions f that model these unknown table configurations. A GCL program has a bunch of variants. The first is assumption, where we assume some formula phi, which we're going to elide the details, but if you know what these things mean, it's a formula in the quantifier-free theory of fixed-width bit vectors. Bit vector arithmetic, Booleans over it with comparison, signed-unsigned comparison, no quantifiers. So we can make assumptions about our code. We can also change the state of a networking packet by assigning to its variables, assigning bit vector arithmetic expressions to its variables, which of course we're going to elide that grammar, but we are going to specifically pull out that we can have uninterpreted functions on bit vectors here. Again, these are how we capture the unknown. We also have sequential composition, which is standard, and this box operator is non-deterministic choice, which I'm not going to go into the details of that, but let's look at an example just to get a sense for how it works. We can encode an if statement into GCL by thinking of if phi then C1 else C2 as syntactic sugar for this GCL program, which non-deterministically runs these two programs. The program on the top assumes phi and then runs C1, and the program on the bottom assumes the negation of phi and runs C2. And what's important here is that non-deterministic choice is optimistic with regard to assumptions. Rather than crashing, like an assert statement might when an assume is violated, we are only going to execute those branches that have satisfied assumptions here. In this example, since phi and not phi are disjoint, we're going to run only one of them for any given input. Okay, so we have this model. And we can rely on largely standard techniques to compile the program into first-order logic. Our first step is lifting, and we're going to elide the details, but the basic idea is that we can produce a formula that lifts out all of our uninterpreted function invocations and leaves us with a GCL program with no uninterpreted functions over our original set of variables that's synchronized using a set of configuration variables. We can use this program to symbolically produce our first-order logic specifications. We use standard symbolic compilation algorithms from Flanagan and Sachs 2001, or if you're not familiar, you can think of this as just Dijkstra's weakest precondition. And this gives us a formula that looks like this. We have phi over our packet variables, our configuration variables. But importantly, the packet variables are universally quantified because those data plane variables, just like in Todd's talk, are not available for static analysis. So this is a precise CI spec. We're almost ready to declare victory. But the problem is that this kind of a specification is not efficient to monitor. And the basic notion is that this set of packets is giant. The set of possible, there are maximum 1,500 bits in a networking packet, which means that if we were to actually think about all of the packets in this finite domain, that would be 2 to the 1,500, which is more than there are atoms in the universe. So we're not going to do that. What we're going to do instead is quantifier elimination. We're going to eliminate this packet variable from the thing that we have to check about our implementations. So basically, we eliminate our quantified variable about the data plane. And this gives us an equivalent specification to our original quantified formula. And this is our precise and efficient CI spec. We prove in the paper that it is precise, which means that it is both safe and weakest. It's efficiently monitorable. When we characterize this formally by defining a syntactic class of first-order logic sentences and showing that they have polynomial expression complexity. And of course, it's decidable because our domain of quantification is finite, but very, very intractably large. So our solution is to use a precise path-based decomposition. We start with a sufficiency check that generates counterexample paths when it fails that we can use to we can hyper-optimize these paths because paths are very easily compressible. And this generates a very small QE instance. We'll pass this to our solvers, which will help us to generate a new candidate specification. And we'll continue this loop until eventually our sufficiency check succeeds. To see how well this works, we collected a suite of industrial and academic P4 programs. P4 is a language for writing these data plane programs. And we checked a standard safety property that's akin to no null pointer dereferences. And for this property, Capiche computes CI specs for most programs in a matter of seconds or minutes. But a few of them hit our 24-hour timeout. But do not worry. Capiche's timeout here actually gives us valuable information about the code. After inspecting these programs closely, we found bugs in the code and in their interfaces. And after fixing them, we could compute specifications in hours or minutes. This has led us to hypothesize that long Capiche runtimes can be considered a kind of code smell, a suspicious observation that likely indicates buggy behavior or poor design. We also checked defined forwarding, which just means that that every packet's forwarding behavior, either that it's dropped or sent out on a specific packet, is defined at the end of processing. And we can do these in just a few seconds to a few minutes. In our paper, you can see our quantitative analysis of our path-based heuristic, as well as our improvement over previous work in the data plane specification inference space. Notably, at the cost of some runtime, assuming our CI specs makes more bugs unreachable than previous data plane spec inference published at SIGCOMM. So let's jump back. We started worried about the unknown and how we can reason about programs in an interesting way with unknown or missing code. Now, with Capiche, we can tame the unknown using a precise CI spec, which precisely describes the implementations of the functions f that cause the program to satisfy its spec. Thanks. I'll take your questions.
Any questions? So maybe let me first ask a simple question. So Yeah, I think it's like a wonderful idea to infer such kind of precise specific specs from the data plane programs. But what kind of programming features of this networking or data plane program can make it efficient, or to make all the work possible? Because the full pipeline, it seems that it also works for general programs.
Yeah, so that's a great question. I can rephrase. What about data planes makes this work? So there's a bunch of features that data plane pipelines have that make this simpler. One of them is tables can only occur in sort of linear. So a table only occurs, functions only occur once syntactically in the program, which gives us more efficient specifications that we would have if they could interact more freely. Another is that they're loop-free programs over a finite domain, which means that we don't have to infer loop invariance, we don't have to worry about complicated loops or anything like that when we generate our verification conditions. And they're over a finite domain, which means that we can do quantifier elimination. So presumably, this kind of approach could work over any domain that admitted quantifier elimination. But I'm not willing to swear to that. That's just an intuition. So yeah, thanks.
Okay, thanks.
Yeah, this is really cool. So as I understand it, packets are like flat big vectors, right?
Yes, yeah, they're bits that you extract from the wire, and then languages like P4 parse them into basically structs that you can use more programmatically.
I see, yeah. So my question is like, is there opportunity to kind of give structure to those flat bit vectors for better verification performance by maybe assuming some faceted parsing or something?
That's actually what makes our compiler optimizations work so well. We can do things like dead code elimination, expression, propagation, in order to sort of basically do a program-level quantifier elimination pass by reducing the size of the program, reducing the number of variables in the program, so that the thing that we actually have to symbolically compile is very compact.
So what you're saying is, if by doing QE, you're kind of imposing structure that you discover on the
Yeah, exactly, because the structure gets a little bit obfuscated when you turn it into a formula.
Great, thank you.
Anyone want to ask a question? Maybe I just ask one more question about the evaluation. So can you go back to the kind of efficiency about the tool?
Oh, this one? Or this one?
Okay, the problem is that, this one. So how efficient would, how large are the benchmarks, and
the programs can be pretty large. These are sort of real industrial grade P4 programs that comprise thousands of lines but have quadrillions of paths through the program. And in our experience, it seems like the number of paths through the program is really what causes performance degradation, not necessarily the length of the code. Because the number of paths through the program determines, especially for things like defined forwarding or no null pointer dereferences, you have to analyze all the ways that you could create valid data or invalid data. And that's really dependent on these complex parsers, which we'll hear about in a couple talks, and how they, in a complicated way, produce data. So it's really the number of paths through the program that makes this more complicated, because that sort of correlates to the number of counterexample executions that you have. But the point is that our path-based heuristic means that we're only exploring a very, very small proportion of those paths, many, many orders of magnitude smaller.
Okay, I see. Thanks.
Yeah.
Yeah. So I think then thank Eric again for the wonderful talk, and
Thank you.
then to come next speaker. Our next speaker is Zheng Yao from Carnegie Mellon University, and he'll bring the talk about FlowCert, translation validation for synchronous data flow via dynamic fractional permissions.
right, cool. Can you hear me? All right. Thanks for everyone for being here. My name is Daniel, and I'm a PhD student at Carnegie Mellon University. And today I'm presenting our work FlowCert, which is our effort to validate the compilation from imperative language such as C to a class of novel architectures based on asynchronous data flow. And this is joint work with Josh and Brian. So as we probably know, I'm sorry. Oh yeah, sure. Is the mic working or? Is this better? Okay. Yeah, so as we probably know, Moore's law is slowing down and various scaling laws in architecture has ended. So as a result, it has become increasingly costly for manufacturers to put like more transistors into the chip without sacrificing power efficiency. So people have started designing specialized accelerators for different applications, most notably GPUs, and more recently, chips for ML applications, such as Apple's neural engine. And in the design of this specialized accelerators, one fundamental challenge is the balance between power efficiency and programmability, because as you specialize the design for a special application, that means that you inherently lose some general programmability. But as it turns out, there's a class of architectures called CGRAs, which stands for coarse-grained reconfigurable arrays, that strikes a pretty good balance between power efficiency and programmability. And the increased interest in this type of architectures is evidenced by many highly cited papers in top architecture conferences. Some of them are focusing on ML applications, and some are focused on ultra-low power environmental sensing applications. So in this presentation, I'm going to introduce briefly one particular architecture called Riptide, but many other CGRAs share similar designs. So as a CGRA, as I mentioned, it has really good power efficiency, but still retains some programmability. So in more specific figures, compared to ARM Cortex-M3, which is a general purpose CPU, on certain applications, it can consume 500 times less power. And compared to ASICs, which are specialized hardware that are usually not reconfigurable, on certain applications consume only 3 times more power. And it's able to achieve this while being able to run arbitrary C function. So in CGRAs, programs are usually represented as these data flow graphs, which consist of these data flow operators that run in parallel and that they're connected to each other via these asynchronous bounded buffer channels. And under the hood, they're implemented as an array of processing elements shown in this colored squares in the figure above. So each of these processing elements is like dynamic configured to function as one data flow operator in the data flow graph above. And they communicate with each other via these on-chip routers. So this design makes the chip very power efficient because it dramatically reduces the data movement cost compared to like a von Neumann architecture CPU where we need to move data constantly between the processor and the cache and memory. And to program these architectures, using data flow graphs directly is difficult, so people usually compile from an imperative language such as C. In the case of Riptide, they compile C programs to LLVM via CLAN, and then to a data flow graph via their custom data flow compiler. And this second step of compilation is very non-trivial because on one side you have a sequential and deterministic, more or less, imperative program, and on the other side you essentially just have a bunch of parallel data flow operators that are connected by these asynchronous channels. And some of these operators can also share a global memory, so you could have data races, and because of the bounded buffers in these channels, you could also have deadlocks. And in a more realistic example, this is the data flow graph that computes the SPLASH'24 hash function, and it has about 180 data flow operators and that's like 180 parallel processes communicating with each other by asynchronous channels. And then it could have data races due to shared memory, and then you could have deadlocks as well. So reasoning about this data flow graph is, at scale is non-trivial. And at the same time, programs in these devices might be deployed for years, such as for like environmental sensing applications. So ensuring the correctness of compilation is very important in this case. So in our work, we designed a translation validation technique to ensure the correctness of each compilation instance. So our tool FlowCert will essentially take the input imperative program and the output data flow program, and then we automatically verifies that they're equivalent, which both guarantees the safety and liveness of the data flow program in the sense that it will produce the right value if it terminates, and also has the same termination behavior as the original imperative program. Okay, so I'm gonna talk about how we do that exactly. So to make the proof more manageable, we split our translation validation technique into 2 steps. So in the first step, suppose we have some LLVM transition system and some data flow transition system that could be non-deterministic. We first pick a particular deterministic canonical schedule in the data flow program, which roughly corresponds to how the LLVM program would execute. This allows us to kind of establish a forward simulation from LLVM to the data flow program. And then the second step, we want to show that this canonical schedule is fully general. So we use fractional permissions to ensure that the memory accesses are consistent, and therefore all the other schedules would eventually converge to this canonical schedule. And for the rest of the presentation, I'm going to give a running example of how we do these 2 steps. So let me start with the first step. So where we want to check that the input imperative program forward simulates the data flow program. So this is an example of compilations. On the left, we have a C program, a source C program that essentially takes in 2 arrays, A and B, and then stores the element-wise increment of A to B. And on the right, we have the compiled data flow program, which is hopefully equivalent to the C function. So under the hood, the C function is compiled to LLVM first, which is also in the input of our tool, so we start from there instead. And the general idea in this step is that we use a particular form of simulation called cut simulation. So the idea is that suppose we have these 2 transition systems, we use heuristics to find a symbolic correspondence between important program points in both programs, such as the exit, entry, and loop headers in the program. And these program points are called cut points. And so these cut points do not need to like include intermediate states because they may not like match on both programs. And then to check that this forms a cut simulation, we check that starting from each cut point, if the LLVM program makes a few steps, then the data flow program should also make a few steps and reach another cut point, in this case, cut point 2. And if we can verify that for each cut point, then we say that there's a cut simulation between the LLVM program and the data flow program, which would imply program equivalence in some sense. So in the case of our example, we essentially need a total of 3 cut points on the LLVM program. One is placed at the entry, the other is at the exit, and then there's a middle one placed at the loop header. And the way we check the simulation is that essentially is that starting from any cut point, so for example, from cut point 2, if the LLVM program executes some instruction, we use compiler hints to figure out which data flow operators roughly correspond to that instruction, and then we would execute that data flow operator on the data flow side. So for example, like if we're executing this comparison instruction on the LLVM side, we would execute this comparison operator on the data flow side, and so on and so forth, until this execution reaches back to the same to another cut point. In this, the same cut point. In this case, the same cut point again. So using this, we're able to check that there is a simulation, a forward simulation from the LLVM program to the data flow program on this canonical schedule that is similar to how the LLVM program executes. And to show that this canonical schedule is fully general, we use, in the second step, we need to use these fractional permissions to ensure that essentially the memory accesses are good. So the reason we need this is that, for example, if we are executing this particular load instruction on the LLVM side, which corresponds to this load operator on the data flow side, it could be possible that some other operator is also available to execute. So in this case, this add operator could also be available to execute. And in general, instead of a simple add operator, this could be a complicated subgraph that has memory accesses. So, so our solutions to tackle this scenario is to use a somewhat dynamic version of fractional permissions. So the general idea is that we would pass memory permissions tokens around operators, such as we enforce that there's at most one writer of a particular memory location at the same time, and there are at most k parallel readers at the same time if there's no writer. And the operators cannot duplicate tokens, so they're used in a affine fashion. And more specifically, these tokens are formally like formal sums of less than or equal to k read permissions per memory location. And you can write to a memory location when you have all k read permissions for a memory location. And to enforce these rules, we essentially attach permission variables to values, input and output values of each operator. So for example, if we have this A operator here, and it has 2 inputs and 2 outputs, so we would attach these permission variables, which stand for unknown permission tokens, to the input values of A. And then once it processes these two inputs and then produce 2 outputs, we would attach fresh permission variables to the output. And then in addition to that, we would add a permission constraints on these variables, saying that the output permissions should be contained in the input permission, and then they should be disjoint. So to incorporate this into our simulation check, we essentially augment our symbolic execution from each cut point with these permission variables. So for example, we would attach P1 and P2 to the input of these 2 C operators. And then once they produce new outputs, we would attach fresh permission variables to the outputs, so on and so forth. And in particular, at the load operator, we would also require that there is at least 1 read permission present in its input tokens. So in the end, we would have collected a bunch of permission constraints, and then we checked that they're satisfiable with respect to some simple fractional permission algebra. And we proved that if it's satisfiable, then there are some good properties about these programs. In particular, if we assume that the LLVM program terminates, then we show that the data flow program should terminate in the same final state. And even if the LLVM program may not terminate, we show that the data flow program should synchronize infinitely often with the LLVM program, assuming the fairness of the canonical schedule. And these meta-theorems are also formalized in a verification tool called Veris. And so finally, we did some evaluation on the Riptide CGRA. So our tool is implemented in Python, and it generates verification conditions in Z3. And so we automatically verify the compilation of all the benchmark programs in Riptide. And we found 8 bugs in their prototype compiler in total, and including a data race that is otherwise hard to discover via simple testing. And performance-wise, our simulation check took less than 1 second for our cases. And then solving the permission constraints took a bit longer, but we believe that it can be heavily optimized with a more specialized solver. So in conclusion, our work is FlowCert, which is a translation validation technique for verifying the compilation results from imperative programs to data programs. And feel free to read the paper for more detail if you're interested. And thank you.
question from the audience. You can just use the speaker in the middle. Just use the speaker.
Okay. So I'm curious how you find the cut points. Could you dive a little deeper into an explanation? Thank you.
Okay, yeah, that's a good question. So, so in our case, like the cut points are found using some heuristics and compiler hints. So essentially, we would kind of place the on the LLVM side, we would first place cut points on like entries and each loop header, and then we would kind of do symbolic executions on the LLVM side to figure out what exactly the data flow program state should be at those cut points. And then that's essentially how we find like the cut points. Yep.
Okay, hello. Thanks for your talk. I have a small question about the trace analysis. So during your data flow trace analysis, how do you know that the two instructions, they are actually read or write to the same memory location? So if I understand that, so you have to do something like the pointer analysis to know that the two instructions, they are actually write to the same or similar or related memory locations.
Yeah, that's right. So that's also a very good question. So like, so in most cases, so we would kind of mark all the memory operations in the data flow graph with like a particular region of memory that it can write to. For example, in this case, the load instruction, load operator would only write load from the like the array A, and then the store operator at the end there would only write to the array B. So essentially, we will only kind of record the permissions for each memory region in a sense. So like we would have like permission tokens for A and a permission token for B, essentially. So that's like some potentially simplifying assumption about the data program, but that's like the heuristics we use.
Okay, actually, so you say, so for example, the line 11. So
yeah.
I mean, you can know that the actual index of the array accessed is maybe the value of I, the variable I. You know that, so you can know so which what memory locations is accessed. Okay, got it. Thank you.
Okay.
Hi, thanks for the talk. Did you say that you can handle arbitrary C programs?
Yeah, so like, so in the Riptide project, they have like a compiler that from like arbitrary LLVM functions to data flow graphs.
Because these kind of data flow diagrams, you said they have bounded buffers between the nodes and they have a finite structure, right? So I'm wondering how you handle like C functions that have use the call stack arbitrarily deep or do stuff with the heap. They don't have a predictable kind of memory footprint.
Yeah, that's right. So right now, I believe they don't have like support for function calls yet. So, but they do support like loops, general loops.
Right.
in
so anything that has like a finite memory footprint.
Not necessarily. I think like you could still have like access like abundant amount of memory like in the loop or something like that. So like the yeah. So like data flow graph in general should be like Turing complete, and you can basically represent any program.
Thank you.
Yep.
Hi, thanks for the talk. You have two kind of, I guess, it seems like simplifying assumptions, the kind of step 1 and 2. My basic intuition is that at each of those steps you might lose programs, right? You might not be able to find the cut, or similarly, you might not be able to reduce to the one execution. Did you ever find programs where that was, supposing that intuition is correct, did you ever find programs where that wasn't the case? And
yeah. Thank you for your question. So yeah, so our like technique is definitely like not like complete. So yeah, so like in our case, like we did have to kind of make, for example, the fractional permissions more expressive in order to handle some cases in the Riptide benchmark. But I don't know an example on the top of my head for your question, but we could maybe discuss after.
Thank you.
Yeah, one final question.
Okay. Thank you for the talk. Can you talk a little bit about the benchmarks that do you have any, or like give me some number? I'm curious about how it is scalable when you generate the verification conditions. I assume the architect is very specific to kind of machine learning applications. What happens if you are facing those like large language model that have the intensive matrix computation, but that works, or how that scales up?
So I believe in our benchmark, like we do have like some examples doing like matrix multiplication and stuff. So for like specific like size of those programs, you can check out like the evaluation section of our paper for more detail. I'd be happy to give more detail after the presentation too.
Okay, thanks.
Thank you.
Okay, let's thank Jin again for his wonderful talk, and yeah, we're glad to see like a very hot discussion among this between the speaker and the listeners. And let's welcome our next speaker, Mingwei from Purdue University, to present. Oh, it's actually a distinguished paper at OOPSLA, like predictive practical static differential analysis of network protocol parsers.
Okay, can everyone? From D. Good morning, everyone. My name is Mingwei Zheng. Today, I'm going to introduce our recent work, PADIF, which is a static differential analysis for network protocol parsers. And this work is done by me and the other collaborators from Purdue University. Before introducing our technique, let me first give some background about network protocol parsing. Network protocols are rules that allow devices to communicate, like the TLS protocol for secure communication, and the FTP protocol for file transfers, and the IP protocol for routing data. Network protocol parsing is a key step where incoming data is checked and broken down. This involves input validation, which checks whether the incoming data satisfies some correct format, and also the field extraction, which extracts some specific field value from the raw data. And once passed, the system uses the data for further processing, like transferring files or setting up a secure connection. Network protocol parsing bugs can lead to serious issues, like security vulnerabilities or system miscommunications. Here is an example of the CV bug in the Bubble protocol detected by our tool. Bubble is a routing protocol exists in both wild and wilderness network, and it is used to find the best routing path for data transfer. Before diving into this bug, let's first understand the correct behavior when receiving a Bubble packet. On the left, there is a valid Bubble packet with update message, and it has a 2 bytes payload with a value 50. The packet is then sent to a server, and the server will store this packet in its buffer, and then it will copy the value 50 into a specific field channel. Finally, the server calls the update route function to update the routing table using this specific channel value. Now, let's see what should happen when the network packet is invalid. On the left, we have another update packet, which is also supposed to have a 2 byte payload. However, in this time, it is empty. So this is an invalid packet. And in this case, the server identifies that the packet is invalid and chooses to either report an error or just simply discard this packet from further processing. However, in the buggy location, in the buggy implementation, the server doesn't recognize the packet is invalid and continues to copy the 2 extra bytes, which is actually not inside the original network packet into the channel field. And this results in that the update route function is called with the incorrect channel value. So this is not a typical buffer overread bug that can cause crashes. The incorrect channel value can lead to wrong routing decisions, potentially increasing the latency or causing any packet loss. And also, it may introduce some security risks. Attackers could exploit this to reroute some sensitive traffic through insecure channels. And so it's very important for the server to correctly parse and validate each packet before further processing and routing. Then let's take a look at the CVE implementation bug. On the right, you can see the packet structure. It has a field type, which is 1 byte, and another length field, which is also 1 byte, and additional channel field. And the length of the channel field is determined by the value of the length field, actually. And the total length size, we define it as packet length. And the packet length should include at least the size of the type field and the length field and also the channel field. So we need to guarantee that the value of the packet length is greater or equal to 1 plus 1 plus length. So it is packet length greater or equal to length plus 2. However, in the buggy code, it checks like in the red code line, it has a if checking if length greater than packet length and return error. So this means that the parser only guarantees that the packet length should be greater or equal to length instead of length plus 2. So this is actually incorrect. Just like the CVE bug we mentioned, many protocol parsing bugs are silent data corruptions, which violate protocol rules but don't crash a system. So traditional fuzzing techniques can often miss these kind of bugs. Model checkers, which need protocol-specific oral code to detect these bugs. But formal specifications are often missing since the network protocols are often described in natural language documents, such as the RFC documents. And so it's very time-consuming to manually construct those formal specifications in order to let model checkers to detect the bug. So the traditional testing tools fail to find this kind of silent bugs. Then how can we catch these silent bugs? We noticed that different platforms like FreeBSD and Linux and also Windows, they have their own implementations of the same network protocols, such as the Bluetooth protocol. And these implementations are meant to provide the same functionality for the same network protocol. And this means that if we find any inconsistency in their parsing behavior, it might indicate some, at least inconsistency, but also it might indicate some bugs, right? So this time we decided to use differential analysis to catch these silent bugs. However, existing stack differential analysis often fails to catch the bugs inside syntactically disparate programs. So like the word graph_diff and the differential symbolic execution, they work well in programs which are semantically very similar. The program looks very similar, syntactically similar programs. But when it comes to syntactically disparate programs, they may fail. And dynamic differential analysis, like the differential testing or differential fuzzing, works by running both implementation A and implementation B with the same input. And then if their execution behavior differs, it can reveal potential bugs. However, these techniques often require high-quality seed inputs to achieve high code coverage. So in the parsing code, to read the buggy code, there might be a lot of parsing input validation check-ins before the buggy line. So the test case need to bypass all those input validation check-ins before reaching the buggy code. And this is actually very difficult because many validation check-ins in network protocol parsings are very complex. So this may lead to the missing of a lot of bugs. And another thing is that when differences are found, they don't directly point out where the buggy code is, and requires a lot of manual effort to check, okay, so where the buggy code is located inside the source code. So to address the limitations of existing differential analysis tools and also the traditional bug detection tools, we need a differential analysis technique that can handle syntactically disparate programs. And we also needed to achieve precise comparison and also offer no-effort bug localization. As we know, parser implementations implement protocol formats. And on the other hand, the protocol formats can also be inferred from the source code. This is done by collecting some pass constraints from successful passing paths. And we can see an example for that. For the parser implementation on the left, there are two successful passing paths, which actually return success in this case. And the first path, I highlighted it in yellow. It has, if one greater or equal to packet length, return error. So it requires packet length greater than 1. And also a checking for the type field. The type field is actually representing the first byte in the buffer. So it requires the buffer at the first byte of the buffer be equal to 0 in order to return success. So we got the pass constraints on the right. The packet length should be greater than 1, and then packet 0 should be equal to 0 for this pass. Another successful passing path, which is also highlighted in yellow this time, it requires packet length greater than 1 and packet 0 not equal to 0, and the packet 1 no greater than packet length. So the protocol formats for this parser is actually made up of the disjunctions of the two pass constraints derived from the source code implementation. And so by comparing the protocol formats from different implementations, we are able to find semantic differences between the parsers. So here is the basic idea of PADIF. We extract protocol formats from different implementations and compare these formats to find any inconsistencies. To discover the CV bug we described earlier, we get another implementation. And then we extract the format from both implementations. Since we represent the protocol formats in first-order logic formulas on packet and packet lengths, we can compare syntactically disparate programs by just simply comparing these two formulas. To compare the two formulas, it seems straightforward to use the SMT solver to check whether phi1 not equal to phi2 is satisfiable or not. And if satisfiable, the SMT solver can give us an input which can be passed by one implementation but failed by another. And this may indicate inconsistency here, right? However, in real-world cases, the format constraints are often very long and complex. The difference itself cannot directly pinpoint where the difference locates. So, and also, this only show one difference at a time between those two formulas. And if we want to, And if we want to get all possible differences, we may need to repeatedly query the SMT solver in order to catch more differences, which is actually very inefficient. So to compare the two formats precisely, PADIF transforms its format into a finite state machine. State transitions in a finite state machine represent constraints on the input, and this is ordered by the buffer indices. For example, in the example here, we have both finite state machines start with constraint on packet length, and then followed by constraint on packet 0, and finally constraint on packet 1. Once the finite state machines are built, we use bisimulation to compare the two finite state machines. We start from the initial state as 0, and then recursively matching states. In the first finite state machine, the state transition starts from S0, and from S0 to S1, it requires constraint like packet length greater than 1. And for another finite state machine, from state 0 to state 1, we have packet length greater or equal to 2. And we give these two formulas into SMT solver and to check whether these formulas are equivalent or not. And here, obviously, it is equivalent. So we can match the two S1 states together. As we continue the bisimulation, we eventually find that the last S4 states cannot be matched. This is because that the state transition from S3 to S4, in one implementation, it requires packet 1 no greater than packet length, and another implementation requires packet 1 plus 2 no greater than packet length. So these two formulas are not equivalent, so we found an inconsistency here. This process allows us to match semantically equivalent constraints while also identify any inconsistencies. Our comparison is both precise and efficient by breaking down the comparison of the large and complex formulas like the phi1 and phi2 into multiple comparisons of these kind of small ones. Each inconsistency we get from the last step is a pair of constraints derived from the source code. And by maintaining a mapping from the source code checkings and the past constraints we derived, when we found the inconsistent here, we are able to trace back into a source code location where the buggy code occurs. So this makes bug localization much easier and low effort. PADIF is built on top of LLVM, compiler infrastructure, and Z3 SMT solver. Although our current implementation mainly focuses on parsers implemented in C, the idea of PADIF applies to parsers in all programming languages. We evaluate PADIF with 14 protocols, and for each protocol, we select 2 different implementations for comparison. And it takes PADIF an average of around 50 seconds to finish each protocol. And this includes lifting both formats from 2 implementations and also transforming the formats into a finite state machine and also do bisimulation and the finite state machine. In total, PADIF found 41 new bugs in real-world parser implementations and with a false positive rate of only 7%. So you can see PADIF is quite efficient in bug finding. More technical details and evaluation results are available in our paper. So in summary, PADIF is able to compile syntactically disparate programs by lifting formats from the implementation source code. And it achieves precise and fine-grained comparison by transforming format into finite state machines and then do bisimulation. Also, it provides low-effort bug localization. Thank you all for listening. Please feel free to scan the QR code if you are interested in our work. Thank you again.
So thank you for your great talk. I have a little bit of question about that. So first, since I think this workflow in general, it can work not only on the network protocol parsers, it can work on many basic systems, like you want to compare program A to program B, if they're equivalent. And second, for equivalent comparison, since you are using finite state machine, it can be viewed as a DFA. Have you considered other methods like clean algebra or some other methods? Thank you.
Sorry, can you repeat your question again?
Okay, the first question is that can your workflow push to other applications other than network protocol parsers?
Okay, let me first answer the first question. You mean that whether we can apply our PADIF into more general testing frameworks, like we evaluate PADIF in some other implementations. I think to this question, I think currently we are only able to handle the comparison of input validation check-ins because we are extracting the past constraints, which is directly from the source code if-else checking or switch case checking. And these past constraints, I think it applies to those kind of parsing or input validation checking, not only to network protocol parsings, but also to the other applications like the media codecs or something. So I think this, the PADIF can be applied to those implementations which have something related to input validation and parsing. So this is for your first question.
Okay, thank you for your answer. So the second question is that since you are comparing finite state machine, have you considered other methodologies to compare them, or why, if you consider, why you don't use them? Thank you.
I think finite state machine is just a data structure to used to breaking down the large formulas into small parts and for comparison. I think you do not need to consider finite machine as a totally different thing. It is just a different data structure representation of the path constraints. So I mean, for any other techniques, it may also use some other data structures to represent the formats in different ways. But the key idea should be very similar. It is still to do the comparison on the path constraints itself in different ways. Yeah.
Thank you very much.
Thank you.
Yeah, thanks. This was really cool.
Thank you.
I have a bunch of questions. I'm trying to figure out which one to ask. So I'm a bit confused about the trend, about how you generate the finite state machines. It sounds like you generate them from this set of logical constraints, the format, which is, and then the finite state machine looked a lot like maybe an AST, a different notation of an AST. Is that a right way to think about it, with maybe some commutativity constraints as well? Or is there something else going on with how these finite state machines are generated? Like, can you have loops in these finite state machines?
I think in our state machine, we don't have loops. It is like, you can maybe take a look at the example here. It is more like, for the format, once we extract it from the source code, it may contain the check-ins on different byte of the input buffer. And the order might not be directly follow the buffer indices, right? So here we just do a reordering. So start from, we are based on this kind of assumptions, like if two formulas are equivalent, then its check-ins on the packet length should be equivalent, and then its check-ins on the packet 0 and the packet 1 should also be similar. So we did these finite machines to, before that, I think it is kind of reorder to make it follow the buffer indices, and then to kind of sort these path constraints and only compare the path constraints related to some specific field or specific byte indices. Yeah, this is what our finite machine do. And regarding to your loop, I think it does not exist here, because for the real world code, source code, we do the loop unrolling to handle different. There are a lot of while loops inside the parsing code, but it is supposed to provide the same semantic constraint on the input buffer. Yeah. So
I have a quick follow-up question, if that's okay.
We're actually running out of time, but
okay, I'll follow up later.
We can just make this discussion offline, because it's fine.
Yeah, I think I will hold a poster session this night. So if you have any further question or any collaboration opportunities, I'm very happy to discuss that with you. Thank you all. Thanks.
Okay, thank you again. Okay, let's welcome our final speaker, Dennis from UMass Boston, to give the talk about sound and partially complete static analysis, data races in GPU programs.
Hello? Hello? Hi. Yep. So, hi, I'm Dennis Liu, and I'm going to present about sound and partially complete static analysis of data races in GPUs. This is joint work with Tiago Cogombrero and Julian Lange. So a bit of background, GPU, graphics processing units, GPUs, are devices that specialize in highly parallel computations. They're used in many sectors such as 3D graphics, machine learning, systems biology. So how they work is they run a large number of concurrent threads on multiple layers of shared memory. So failing to reason about correctness when writing GPU programs can lead to concurrency errors, such as data races. So what is a data race? It happens when two or more threads access the same memory location, and at least one of those threads are writing to that location. So data races cause undesired non-deterministic behavior, memory corruption, and program crashes. So there are two main ways to handle data races. One is we create a data race freedom verifier, which verifies the absence of data races in the program. So we check that no data race exists in all possible execution paths. The other way is we create a data race finder, which detects the presence of a data race and finds and reports the program execution that leads to that race. So the main property of a data race freedom verifier is to check data race freedom. So we can define soundness as if the tool proves a data race freedom, then the program must also be data race free. So no false negatives. And completeness is the opposite, where if the program is DRF, then the tool must be able to prove DRF. So no false positives. Data race finders are the opposite of that. So soundness in a data race finder is if the tool proves a data race, then the program must also have a data race. No false positives. So completeness is when the program has a data race, then the tool must be able to prove that data race. So we see that it's like the flip side of each other. So for this presentation, we're going to stick to the data race freedom verifier definition of soundness and completeness. So completeness just means no false positives, and soundness, no false negatives. So most DRF verifiers are sound. They aim to be sound. So we can trust when the tool reports DRF. But however, when the tool reports data races, they can be impossible data races in the program. So this leads to false alarms, and we consider that incomplete. Data race finders aim to be complete, so we can trust a data race finder's reports of data races. But when a data race finder reports a DRF, they can miss actual data races, so it's considered that false negatives, and they're normally unsound. So most DRF tools are usually static checkers. They check without running the program, which are approximations. Examples of such tools are File, GPU Verify, and Pug. Data race finders are usually dynamic, usually under approximations of the program. Examples of these are HiRace, HACCRG, and Scored. So you want to build upon our previous two File to keep the sound data race free reports while tackling the incomplete data race reports to be partially complete. So in this paper, we present File AA, which is a static data race finder for GPU programs, while also maintaining the capabilities as a sound data race free verifier. So we characterize a class of programs where our analysis only produces true alarms. We find that to be around 60% of programs. We formally established the root causes of false alarms in File AA, so to determine the sources of approximation. So the structure of this talk will be in two parts. Firstly, the empirical results of File AA. We asked two questions. Can File AA verify bug fixes in open source projects? And does File AA have fewer false alarms than the state-of-the-art? Second part is the theoretical results, mechanized in about 16,000 lines of code, code. I'm going to present about control flow independence and data independence, and then establish our true positives theorem. So the first question, can File AA verify bug fixes in open source projects? We found 6 bug fixing commits from GitHub, from OpenMM and Megatron LM. So we want to run the state-of-the-art on the buggy version of the commits and then the fixed DRF version of the commits. So here we have 3 tools, file AA, file, and GPU verify. Firstly, we run on the RACI buggy version. So we preferably want a high number of true data races or potential data race reports and no data race free and crashes. And we find that file AA has the highest true data races and potential data race reports, so all of them are reported as data race. We see that file crashes on most of them, and GPU verify even reports 2 as DRF, so that's an unsound report. And we notice that only file AA is able to report true data race reports out of these tools. So for this fixed data race free version, preferably we want DRF reports and no data races and crashes. So we find that file A reports the highest number of DRF and does not crash on any of them. So we can able to confirm 5 out of 6 programs. So for the second question, does file A have fewer false alarms than state-of-the-art? So to do this, we reproduce an experiment by Bardsley in CAF14, where we have 226 reportedly DRF programs from NVIDIA and Microsoft and some simulation benchmarks. So again, we run the 3 tools on this data set. So preferably we want, since this is a supposedly DRF data set, we preferably want a high number of DRF reports. And we find that file AA is the highest among the 3 at 93%. Also, we have the lowest amount of potential data race reports at 1.8. So approximately 1.9 times fewer potential alarms than the other tools. The second important thing is that we were able to find 10 undocumented RACI programs, so true data race reports in this well-studied data set. And 6 of these programs are both missed by file and GPU verify. So let's formalize the sources of false alarms. Here's the pipeline of our tool. So we take a CUDA program, inference that into a memory access protocol, and then finally quantify into a SMT formula. So a memory access protocol is a type that codifies the behaviors of threads over shared memory. For scalability, memory access protocols abstracts away what is written to and read from arrays. So the contents of arrays are lost during the inference process from CUDA to maps. And it is that inference that causes the approximation in our analysis, leading to false alarms. So here we have an example of a GPU program. It takes an input array A, reads from A, and then writes to A. We classify this as a control flow independent, data independent protocol. So that means that the inference process from CUDA to maps is exact, it has no approximations, and that the contents of A is independent to our analysis. So here we have a variation of that program. So the write now is in the conditional, and that conditional is dependent upon what is being read from A, the contents of A. So we call this a control flow dependent protocol. So this write access may or may not execute depending on what is in A. So the reachability of this is inexact. So thirdly, we have another variation. So the write is now writing to what is being read from A in that variable J. We call this a data-dependent protocol. So the reachability here is exact, but the exact index location in which we're writing to is inexact, and it's dependent on A. So how common are CIDA programs? So we had a data set of 2,700 programs, real-world programs. We retrieved this from GitHub. We find that around 59% of real-world programs are CIDI, so our analysis is exact for these programs. So we have how does control flow independence work? We have a type judgment that states that the control flow of the memory access protocol is unaffected by symbolic variables. And also for data independence, which states that the indexing expression of protocols is unaffected by the non-deterministic variable declarations. And we established some theorems for action set correspondence. So the first theorem basically is our soundness property, which states that any access we find in the program is also in the memory access protocol. Second one is that if the memory access protocol is control flow independent, then we know that all the accesses are reachable in the program, but the indexes may be imprecise. And the third one is that if the memory access protocol is data independent, then the accesses are precise. The index are precise, but it may be unreachable in the actual CUDA program. And finally, if the maps is both control flow and data independent, then all the accesses in maps are also in the CUDA program. So now we can finally establish our true positives theorem, which states that if the maps is control flow and data independent, then any data race we find in maps must also be in the CUDA program. So we've now characterized the class of programs as the IDI programs, where our analysis can only produce true data race alarms. So to conclude, I presented an approximation analysis, which is a static technique to detect true data race in GPU programs. It uses 2 dimensions of preciseness, CIDI. We established a true positives theorem, which identifies the class of programs where our analysis reports only true alarms. We implemented these techniques into FileAA, which is the first sound static DRF verifier. There's also partially complete as a data race finder. So our evaluation on FileAA shows that it emits 1.9 times fewer potential alarms. And we found 10 undocumented data races in a well-studied DRF dataset. We confirmed 5 bug fixing commits in real-world open source projects. And our analysis is exact on 59% of kernels. Yeah, thank you.
Any questions from the audience? Maybe let me just ask some simple questions. So you say like the approach is partially complete. So in what sense is that partially complete? Like, is that complete for the specific class of programs? Or?
Yeah, so for specific CIDA programs, we know for sure that all reports are true. But if they are not within that class of programs, we can't be trustworthy on the reports. But we do know the sources of where the approximation may come from.
Okay, so maybe I'll ask one more question. So do you consider like to design a domain-specific language based on your observation? So the programmer, if they use your DSL, then it's guaranteed to be CIDI, and so you can directly use the analysis to find true positives.
Yeah, if the program is CIDI, then yeah, we can confirm the true positives.
So if like you can design a domain-specific language, it's also doable?
Yeah, we haven't looked into that, but yeah.
And any more questions? Yeah, thanks.
Thanks for the great talk. May I ask what makes the GPU program so special? Can similar techniques be applied to such as like CPU programs in general?
So GPU programs they run parallelly, so we have to reason about how it executes in parallel. So that's a bit that's what makes it different from CPUs. There are also different levels of memories. So that's what makes it special, I guess.
Thanks.
Yeah.
Any more questions? Okay, so thanks again for the wonderful talk. So now, then our morning session just ends, and I think everybody can go to have lunch and then wait for the afternoon sessions. Thanks.
time to get started. So welcome to this session on static analysis and program verification. So the first talk we have is about dynamic taint analysis and will be given by Chanyu.
Okay, thanks for the introduction. Hello everyone, my name is Tianyi Liu, and I'm glad to be here to talk about the hard taint production run dynamic taint analysis via selective hardware tracing. And all the authors of this work come from Nanjing University. First, let me introduce some basic backgrounds about the taint analysis. There are typically three key concepts. Taint sources are used to mark the origin of the tainted data, and taint sinks are points where the corresponding taint status is checked to determine where a potential risky behavior has occurred based on the specific application. And taint can also propagate according to the semantics of the program instructions. Taint analysis is widely used in various fields such as bug detection, program diagnosis, privacy, and software security. Compared to static taint analysis, dynamic taint analysis offers higher precision. It dynamically maintains taint information within the program during runtime. However, dynamic taint analysis suffers from high runtime overhead, so it only works for debugging and testing environments and cannot be used for production run usages. To reduce the runtime overhead of dynamic taint analysis, existing works can be broadly categorized into three types. The first type utilizes program analysis to reduce unnecessary taint tracking code. However, due to the inherent limitations in the soundness and completeness, the performance improvements are limited. And the second type uses specialized hardware components to collect information and speed up the process of taint propagation. Such approaches, however, struggle to accommodate a wide range of taint analysis requirements. And the third type decouples execution by separating taint propagation from the source program and offloading it to other processes. Unfortunately, these approaches suffer from high online taint information collection overhead and also increased the latency of the analysis. Despite the above approaches, their runtime overhead on the spec benchmark still ranges from 170% to about 300%, which is far from production use. To further accelerate taint analysis, our insights are that modern hardware tracing models offer the capability to capture the execution information, for example, the control flow and the values of registers with very low overhead. And besides, we can follow the decoupling design, leverage hardware-based tracing to collect taint information online, and do taint propagation on the fly. Although the idea is simple at high level, doing this efficiently and precisely is non-trivial. There are mainly three technical challenges. First, even we are using the hardware tracing all the taint information still leads to high runtime overhead. And secondly, naively recording the intensive taint information via hardware results in severe data loss. And this is because the bandwidth of the hardware trace output is limited. And third, performing taint analysis on the massive scale trace data is costly and efficient. For the first two challenges, we need to use static analysis to reduce the amount of data collected from hardware. And for the last challenge, we do the taint analysis in parallel to reduce the latency of taint analysis. To address the above challenges, we have designed and implemented the hard taint system. Here shows the workflow of hard taint. We have proposed a static identification analysis that, based on the taint configuration, it analyzes the necessary taint information to be traced in the program. Then we rewrite the binary so that the hardware only traces the data of interest. The rewritten binary will be executed on a CPU that supports Intel PT, generating the corresponding trace data. In the real-time parallel, use high-speed RDMA network to immediately transfer the generated trace data to another host, and for parallel decoding and parallel taint analysis. We consider the time gap between the trace generation ends and taint propagation completes as the analysis latency. And let's use a toy example to illustrate how hard tent works. First, figure A is a snippet of the original binary code. To perform tent analysis, we need to trace the path of data transferring. So we need to know the control flow transfer and the memory addresses that have been used in the program execution. If we naively tracing the tent, we would need to consider 7 points in total. That are the branches and the memory addresses used in the binary, and they are marked red in the right figure. However, after our static and identification analysis, only 3 points needs to be traced. And based on the trace point information, we insert statements at the corresponding locations in the binary to record the values. After that, upon execution and decoding, we obtain the corresponding tent data. As shown in figure F, we could know the value of the EX register at L1 from the trace output, and the program control flow takes the L6 branch. And finally, this information is mapped back to the static tent graph, where tent propagation starts from the tent source, and the tent status is then checked at the tent sync node, filled in the orange color. Next, we will elaborate the key technologies in hard tent. And the first is the static identification analysis. Exact control flow are essential to dynamic tent analysis. One of our insights is that not all memory addresses or instructions involved in tent analysis must be recorded. So we consider filtering out unnecessary information from tracing. The 3 main optimizations are used to reduce redundant information from register values, blocks and functions, and loop iterations. In the first optimization, redundant registers elimination, we built value flow graph for each function, and we will only fetch the root register in each weakly connected component of the graph, and other register values could be inferenced from the fetched register. The second optimization is redundant blocks and functions elimination. Only a few basic blocks and functions are relevant to the tent, so we can get the reduced control flow graph by removing tent unchanged blocks. And on the other hand, if one basic block is recorded, the execution paths of other blocks could also be influenced if there are dominance relationships between them. So we can also remove the blocks and functions that could be influenced. And in the third optimization, we also found that a large amount of trace data is generated by just a very simple loop, similar to a memcopy or a string compare function. If the loop is control flow independent, we can trace the control flow just once. And if the loop is data independent, we can also trace the register values just once. The idea is also simple, but is effective in the real-world applications. And after identifying the points that need to be traced, we perform a selective rewriting of the binary. This allows the hardware to selectively trace the tent information we are interested in. Here we use the PT-write instruction provided by the Intel PT to record the required register values. And since the trace data of Intel PT is highly compressed and cannot be directly used for analysis, a decoder is required to recover the tent information. However, the current decoders only support sequential decoding, take a acceptable time for processing the huge trace data. We observed that there are many synchronization point packets, that is called PSPs, in the trace data, and the data between synchronization points is independent. And therefore, we partition the trace data as these PSP packets and assign a decoding thread to each partition. After decoding the trace data, we are going to perform the tent propagation. In the last step, the trace data is split into partitions, so it's straightforward to do tent analysis for each partition in parallel. But since the tent analysis partition may have data dependencies from its preceding partitions, it has to wait the preceding propagation to complete. In hard tent, we propagate the tent status with best effort. If the dependency of a node could not be satisfied, it will be connected to a dependency graph and wait for the preceding propagation. And finally, about the implementation, we utilize the existing tool to implement static analysis, binary writing, hardware tracing, and parallel decoding, and also the taint analysis. We have also conducted evaluations on a rich set of benchmarks, and we intend to address the following 4 research questions. How well does hard taint perform? How about the impact of runtime selective tracing and real-time parallel analysis? How does hard taint perform compared to the state-of-the-art approaches? How effective is hard taint in detecting taint vulnerabilities? First, let's look at the overall performance of hard taint. In terms of runtime overhead, hard taint only introduced 8.6% runtime overhead on average, and it can timely report taint analysis reports with an average absolute latency less than a half second. We also evaluated the impact of varying numbers of threads on the throughput of taint analysis. The average throughput increased gradually with the number of available threads. And at 32 threads, the analysis throughput exceeds or approaches the one of the trace generation, and the high throughput supports to realize the low latency of analysis and timely analysis reports. To understand the impact of runtime selective tracing and real-time parallel analysis, we compare hard taint with software-based tracing and naive hardware tracing. It shows that hardware tracing significantly reduced the runtime overhead from 500% to 82%, but suffers from severe data loss. Further, utilizing identification analysis and selective tracing leads to a further runtime overhead reduction to only 8% without losing any data. We also conduct the comparisons between hard taint, strike taint, and taint pipe, the state-of-the-art decoupling approaches. Thanks to the holistic design, hard taint outperforms strike taint and taint pipe 20 times and 17 times faster, respectively. The relative analysis latency is also significantly smaller. Finally, we also evaluated the effectiveness of hard taint. We considered 8 real-life CVEs, and hard taint can successfully detect all of them. And that shows the capability of the precise taint detection. And to sum up, we have developed hard taint, a system that can realize ultra-low overhead and precise dynamic taint analysis. We adapt a hybrid and a systematic design which combines static analysis, selective hardware tracing, and parallel graph processing techniques to address the challenges. And evaluations also shows that the low online overhead and analysis latency of hard taint, and also its effectiveness. Yeah, and thanks for your attention. I'm ready for any questions. Thank you.
Thank you, Chanyi. We have plenty of time for questions. So maybe I can start. So can you say something about the kind of hardware support that you are taking advantage of here?
Oh, yes. We are using the Intel PT that is, and we are using the PT write instruction that comes from the 12th generation of the Intel CPUs. And it's also possible to use other hardware like ARM chips. It's also okay, but the current implementation of the ARM CPUs will drop about 90% of its trace data. That's the taint analysis will not be precise enough.
Oh, very nice talk. For the binary rewriting that you do you use an off-the-shelf binary rewriting tool, or do you have like your own specialized tool?
We are using the DYInst tool.
One more time?
That is called the DYInst.
Okay. I don't know that tool. Okay, that's why I'm pausing. All right. But that's clearly not your tool. You're using somebody else's.
Yes,
yeah.
yes.
Okay. Very good.
Any other questions? Okay, so I have one more question then. So do you think some of these ideas could be used for also getting efficient taint analysis for more high-level languages? Or is this very much tied to the binary code?
High-level languages. Yes, but the identification analysis needs the whole control flow graph to be static. And if there are too many dynamic features in the language, we must do many special judges on the trace points, and it will significantly increase the overhead. Yes, and I think for currently the hard taint is able to use with maybe CPP and Golang is also okay. Yes, but I think Java Python is not good.
Thank you. Any further questions? If not, let's thank the speaker again.
Thanks.
Okay, so we are a bit ahead of schedule, so let's take a couple of minutes break before we continue.
Okay, good afternoon, everyone.
Sorry, let's wait a minute.
Sorry.
Wait 1 minute. Okay, so let's start. So the next talk is about escape analysis for Go, and is given by Bo Yao.
Thanks for the introduction. Good afternoon, everyone. I'm Bo Yao Ding from USTC. It's my pleasure to be here today to present our research work, MEA2, a lightweight field-sensitive escape analysis with points 2 calculation for Golang. Escape analysis is a method for determining the dynamic scope of pointers. That is, where in the program a pointer can be accessed. Escape analysis allows for optimizations such as stack allocation and scalar replacement. By performing this kind of optimizations, object allocations can be reduced, which reduces the pressure on garbage collection and improves the program's performance. For this reason, escape analysis is widely used in managed languages, such as Java, JavaScript, and PHP, and today's main focus, Go. Go is a young and popular programming language, and it has two main features: native support for high concurrency and efficient development. On the one hand, to support high concurrency, Go's execution unit, the Go routine, is designed to have a lightweight and movable stack. The stack can dynamically grow and shrink during runtime as needed. However, this increases the chances of dangling pointers in the program. On the other hand, to improve the development efficiency, Go employs a garbage collector to automatically manage memory at runtime. However, using garbage collection leads to more heap allocations and affect the program's performance. Therefore, Go proposes two pointer usage environments and introduces escape analysis to check the violation of the environment. For stack objects that violates this environment, they will be allocated on heap. However, Go's escape analysis is implemented on AST and lacks various sensitivities and points to information. This results in a more conservative algorithm with lower precision, leading to more objects being allocated on the heap and resulting in a poor performance. First, Go's escape analysis is field insensitive. In this example, we declare x with type x, and the address of I is assigned to x.p1, and while x.p2 is assigned to a global variable sync. From a field insensitive perspective, the algorithm doesn't distinguish between objects and their fields, leading it to believe that the address of I is passed to sync via x, resulting in the unnecessary heap allocation of I. Secondly, Go's escape analysis doesn't attempt to calculate the points to set for pointers. For example, here, we can know that PC points to C, and PD points to D, and PPD points to PD. In the last line, the value of PC is assigned to PD through dereferencing PPD. But due to the lack of points to information, Go's escape analysis assumes that PPD could point to any location, conservatively concluding that C might be referenced by an arbitrary by a heap pointer, leading to the unnecessary heap allocation of C. To understand the impact of the aforementioned shortcomings, we conduct a simple empirical analysis about memory access operations. And we found that field access and indirect memory access accounted for over 50%, with proportions of 33% and 19% respectively. This suggests that incorporating field sensitivity and points to calculation into escape analysis offers a great opportunity to improve the precision. So we propose an improved escape analysis algorithm called MEA2. It combines type constraints to achieve field sensitivity and integrates the calculation of points to sets. Additionally, we propose a general and configurable representation for function summaries to facilitate the inter-procedure analysis. MEA2 is designed based on Go LVM, which takes LVMIR as input and constructs an escape graph based on it. After simplifying and propagating escape states in the graph, stack allocation is applied. First, we'll start by introducing the abstraction of LVMIR. We characterize variables into two types, top-level variables and address-taken variables. Top-level variables include virtual registers and global variables, and address-taken variables represent objects allocated in the program. For the instructions and the statement, we focus only on 7 memory-related operations: allocation, cast, store, load, get element pointer, find nodes, and co-instructions. Each variable V has an escape state, denoted as ESV. We can define a simple escape state lattice, where no escape is less than escape. MEA2 requires the escape states of variables meet certain constraints. First, for each pointer P points to O, the escape state of P must be less than or equal to that of O. In the case given here, the global variable global PTR points to the local variable VA, and since the state of global variables is initialized to escape, according to the constraint, the escape state of the variable VA can only be escape. The next constraint stems from the specific requirements of Go for objects allocated within loops. If they are referenced by a pointer in the outer loop, they should be marked escape and heap allocated. the escape graph is a directed weighted graph. The nodes are characterized into two types: reference nodes, which represent top-level variables, and object nodes, which represent address-taken variables. The edges are also characterized into two types: flow edges, which use weights of 0 and -1 to represent copy and address of relationships between variables. Field edges indicate that the source node is a field of the destination node with a specific of set X. This figure shows a simple escape graph, and it conveys the following information. The object OBJ has two fields with offsets 0 and 16. Its address is assigned to A, and the value of A is assigned to B. First, we will introduce the rules for constructing the escape graph for field insensitivity. For the new instruction, assuming the object being allocated here is OI, we will add a flow edge with a weight of -1 to indicate that the address of OI is assigned to P. For the cast instruction, when P is a pointer type and Q is not, this can be considered as converting an arbitrary value into a pointer, and we perform a derive operation on P. The derive operation is used to represent unknown pointee. As shown here, the derive operation will create a virtual object node, OV, to represent the pointee of P and mark it as escape. In other cases, we treat the cast as a copy operation. Next, the rules for the load instructions are also divided into two cases. When the pointer set of P is empty and V is of pointer type, we consider that we may point to an unknown object, and thus we perform our derive operation. When the pointer set is not empty, we establish a flow edge from each pointee O to V, indicating that the value of V is assigned to O. The value of O is assigned to V. Next, we will introduce how to calculate the pointer set. Under field insensitivity, we can assume that if the address of O is assigned to P, then O belongs to P's pointer set. According to the definition of escape graph, the points to relationship can be represented in the graph by a path from O to P, where the first edge is a flow edge with a weight of -1, meaning the address of O is taken, and the rest are flow edges with a weight of 0, meaning the address of O is passed to P. As shown in this example, the left code snippet includes 3 instructions based on the rules for the new and the cast instructions. We first establish a flow edge from OBJ to V, and then create an edge from V to C. For the load instruction, we first calculate the pointer set, and we can find that there is a path from OBJ to C, starting with a flow edge of weight -1, followed by a flow edge of weight 0, which means C points to OBJ. Thus, we can establish an edge from OBJ to LD, according to the early rules. The rules for store instructions are similar. When the pointer set of P is empty, we conservatively consider that the value of V is passed to our heap object. Otherwise, we can consider that there is an assignment from V to the object pointed to by P. Next, for the find instruction and get element pointer instructions, we will just consider them as assignment. Next, in the context of field sensitivity, we will need to introduce the concept of type compatibility first. We see that variables V1 and V2 are type compatible if they have the same underlying data layout. For example, although V1 and V2 have different types, they have the same size for each underlying data field and can be converted to each other. Thus, we say they are type compatible. And then we can define an assign operation to handle the assignment between two typed variables. If they are type compatible, corresponding flow edges will be established between each of their respective fields. And otherwise, we consider that they cannot be safely assigned, leading to a conservative approach. Next, we will introduce the calculation of the points to set for field sensitivity. We introduce the constraints of type compatibility to refine the points to information. Consider the following example. OBJ is of type T1, and C obtains the address of OBJ through V. At this point, there are three object nodes whose address equal to the value of C, obj, obj.0, and obj.0.0. Among these, obj.0.0 is compatible with the I8 star type, and therefore C points to the obj.0.0, and we can finally add an edge from obj.0.0 to LD. In the context of field sensitivity, the rules for load and stores are modified as follows. The calculation of points to set and assignment or assign operation is adjusted. Finally, we will talk about the rules for get element pointer instructions. When the point to set of P is not empty, for each object that P points to, we will create a new object node O.X and add a corresponding field edge to represent that O.X is the field at offset X of O. Additionally, we add a flow edge from O.X to F with a weight of -1. And as for interprocedure analysis, MEA2 adopts a function summary-based approach. Function summaries are records of data flow relationships between parameters, return values, and heap objects. Each function summary is a combination of flows. The design of flow is as follows. It consists of a source access path and a destination access path. Each flow represents an assignment between the node accessed from the source access path and those accessed from the destination access path. For example, here is a function called JC_WriteBarrier, which performs a store operation from parameter Q to P. Its corresponding escape graph is shown on the right. We can see that there is an edge from Q to star P, which is the content that a flow needs to record. First, it records the access path from star P to P, and indicating how this node is accessed through P. Secondly, it records the access path for Q as the source access path. Based on the summary, we can define the construction rules for code instruction. For a code instruction, we first retrieve the summary of the code function. For each flow in the summary, we identify the nodes accessed by the access paths and perform assign operations between the source node and the destination node. For example, in the following case, the full function calls JC_WriteBarrier. Before analyzing the code statement, its escape graph looks like this. Based on the summary of function, we can first locate the source operand V accessed by the source access path, and then identify the destination operand OBJ based on the destination access path. And finally, we will add an assign operation between them. And finally, we evaluate MEA2 on dataset consists of 12 widely used open source Go projects. First, we attempt to evaluate the effectiveness of MEA2. We compiled the source code in the projects using GoEA, which means Ghost Escape Analysis, GLEA, which means Go LVM's escape analysis, MEA2, that's ours, and the field insensitive version of MEA2, namely MEA2FI, and counted the number of heap allocation sites in the generated code. The first chart below here shows the total number of heap allocation sites for each project. And the second chart shows the proportion of heap allocation sites reduced by MEA2 compared to other algorithms. We can see that MEA2 results in the fewest number of heap allocation sites, and compared to GLEA, heap allocation sites is reduced by 7.39%, and compared to GoEA, heap allocation sites reduced by 6.83% in average. Secondly, we conducted dynamic tests to evaluate whether programs compiled with MEA2 could achieve performance improvement. Since MEA2 is implemented based on GoLVM, we use GLEA as baseline. We selected 46 memory-bounded unit tests from the projects as test sets, and collected runtime statistics by compiling and running them. The results are shown in the graph. On average, programs compiled with MEA2 reduced execution times by 2.04%, garbage collection frequency by 29.29%, maximum heap size by 15.5%, and total heap memory allocated by 16.3%. Okay, that's all. Thanks for your time.
Thank you. Any questions?
Sorry. Thanks for your talk. That's very great. So I have a question about your motivations or the difference between the traditional escape analysis on C or C++. I mean, so actually your work is conducted over the LLVM framework. So my question is, so what's what's the difference between the traditional escape analysis on C and C++ and your analysis on the Go program languages?
I'm sorry, due to the time limitation, I have hide this page.
Okay.
There are many existing works on Java about escape analysis.
Okay.
But I think the difference is Go offers a different memory access paradigm differ from Java, because in Java every field is a reference, and in Go he's like C or C++, and his field can be a subject of the object of field can be a subobject, and any field can be referenced. This makes a difference from Java. And as for C++, because there are not escape analysis work about C and C++, because they are not garbage collected.
Okay, thank you for answering. So I have a follow-up question. So can you just directly use your current framework to analyze the C++ code? I mean, there could be some kinds of similar features like the fields or the pointers, the objects in C++. So
actually, because our work is based on GoLVM, it is based on LVM-IR. So I think actually it's the same.
Okay.
No matter C, C++, or Go.
Okay, thank you.
I have a question also. So how does this points-to analysis relate to more traditional points-to analysis techniques like subset-based Anderson-style analysis?
Compared to traditional points-to analysis, this is faster, because escape analysis doesn't require to compute the point-to set of global variables. They just compute some point-to set of local pointers. So there are many conservative handle of the in my algorithm, like here sorry. Oh, sorry. like the derive operation I have just talked about for any object that may be allocated outside the function. I will just use our virtual object, and this will simplify the point-to-set computation.
Thank you. Let's thank the speaker again. All right, next talk is about Newtonian program analysis of probabilistic programs. Please go ahead.
Okay, and thanks Andrew for the introduction. And can everybody hear me? Okay, great. So yeah, good afternoon. I'm D1 from Peking University, and today I'm very glad to have this opportunity to present our work on this so-called Newtonian program analysis of probabilistic programs. And this is basically based on a collaboration with Professor Thomas Reps from University of Wisconsin-Madison. So let's first review a typical pipeline of data flow analysis using example program shown on the slide here. The program is a very simple imperative program which defines a recursive procedure X. The program is probabilistic in the sense that it makes some random choices to determine its actual control flow. For example, as marked in yellow on the slide, prob 1/3 makes a random choice so that the conditional branch takes the then branch with probability 1/3 and the else branch with probability 2/3. In the else branch, you basically make two consecutive recursive calls to the procedure X itself. The program analysis pipeline usually can turn the program into a suitable IR, for example, a control flow graph. On the control flow graph, we allocate each control flow edge with an action. For example, random choice with probability 2/3, which I just write like P with 2/3 on the control flow graph, and also like the procedure call to X, which I allocate call X as the control flow edge action. Next, the pipeline can use an abstract engine to turn the control flow graph into a data flow equation, usually with a suitable algebra such as semi-ring. The solution to this equation corresponds to a particular program analysis. For example, the termination probability of the procedure X. And using some proper solver, we can solve the algebra equation shown on the third card that, okay, the procedure X shown on the first card, it will terminate with probability 1/2. In an interprocedural setting, the data flow flag can also serve as a procedure summary for X, which means that whenever you call X, you can directly use 1/2 as the termination probability. This pipeline we just reviewed corresponds to the well-studied functional approach to interprocedural data flow analysis. Suppose that we want to analyze a program with multiple procedures. And as the pipeline showed in the previous slide, we can establish a system of data flow equations where each unknown variable xi stands for the summary of the procedure pi. We can then solve the equation system by a generic iterative algorithm to find successive approximations, such as the cleaning iteration. As demonstrated here by the animation, we start from some bottom element in an abstract domain, and we approximate the solution iteration by iteration. So in terms of the termination probability analysis, we can first interpret the equation using the abstract semantics for termination probabilities. Basically, it's a domain of real numbers from 0 to 1. For example, we can interpret the program action skip as probability 1 because the program skip always terminates and the atom prob 1/3 with probability as the probability 1/3. Then the algebraic operations, the extend or the circle times, we just reinterpret it as multiplication because the extend means the consecutive composition of two programs. So termination probability of two programs we can just calculate it by a product of the termination probability of two programs. Then for combine, which I just use the circular plus, which means we just interpret it as the addition of probabilities, because for combine, it means we want to combine the two different control flow paths on the control flow graph. So we can just sum up the termination probabilities. So after we replacing all the algebraic operations with the Euro numeric operations, we obtain a standard numeric and also quadratic equation. And if we use clean iteration, we reviewed in the previous slide, we obtain an infinite sequence of successive approximation from 0 to 1/2. Note that we can it can take like an infinite number of iterations to reach the final answer. But for this kind of numeric equation, there's another generic solver based on Newton's method. So does everybody like in this room already be familiar with Newton's method? Okay, so I think I can speed up this, but just to recap some of the essentials, it's also like an iterative algorithm which makes successive iteration to compute the root of a function. So the idea is that for given a function f, we can construct like a linear model of the current approximation. So for example, we start with xi, we compute the derivative of fxi, then we construct a tangent line through the point xi, fxi. And then use the crossing of the x-axis and this tangent line to be the next approximation, xi plus 1. And we just repeat the process. Okay, then we are approaching the actual root just like by repeating the whole process. But you can still notice that like we still need an infinite number of iterations in theory. But how does that go back to the termination probability analysis? The simple way is that we can move the left-hand side to right-hand side, then we can obtain a function f. Then we just reduce the termination probability analysis to finding the root of this function f. So we just repeat this process, so we can construct like another sequence, which I just knew here, another infinite sequence of numbers, and finally we will reach the true answer, 1/2 as the termination probability. But both clean iteration and Newton iteration, as I said, they all cause like an infinite number of iterations to converge, but which will converge faster in practice. So just plot like the two sequences we just seen for the termination probability analysis, and the blue one stands for the clean iteration, and the Newton one and the orange one stands for the Newton iteration. And as you can see, because the ground truth is 1/2, and a Newton iteration can converge faster than cleaning in this setting. So can we apply the Newton method as a generic equation solver to program analysis? The answer is yes. In 2008, SPLASH' et al. Proposed Newtonian program analysis, which applies Newton's method to interprocedural data flow analysis. The overall idea is that this is the basic scheme for cleaning iteration, but for Newton iteration, we want to construct a linear correction term per every iteration, and the high-level idea, we can also demonstrate this kind of Newton iteration visually by, so one Newton iteration will basically make multiple cleaning iteration, and then it will converge to the final solution with fewer steps. Then, so how does this linear correction term be constructed? So the idea is that we can just define some syntactic linearization, which is very similar to the derivative from the calculus. Because now, if we think of a semi-ring contains both like a multiplication and an addition operator. So we can just define this syntactic linearization rule. Similarly, for example, the sum, the derivative of a sum is basically the sum of derivatives, and then the derivative of a product is basically we just follow the standard Leibniz rule to define the syntactic linearization. No, all of those don't need to have any concrete meaning because they are just syntactic. Then in the Newton iteration for program analysis, we just construct a linear equation in every iteration. And here I just change the unknown variable from x to y. And as you can see, like for each, at the highlighted part in the yellow, this is the linear correction term, which, and this is how it's actually defined. So the basic idea is that we compute the derivative of the function at the previous solution to the equation, and then we just use that to construct a linear function by multiply it by y to construct a linear model of the original equation. But I have to note here is that this form is inexact, and just use it for brevity, because in general, a same ring does not have to be commutative. But if we assume like the extent is commutative, then we can obtain this form here. And to see why this is a linear correction term, for example, if the original function is x times x, and I want to find its linearization at nu, it will become x times nu plus nu times x. As you can see, if like the multiplication is commutative, you would basically get to like 2 times nu times x, something like that, as what we can see from the calculus. And also for another example, if we want to compute the derivative of b times x times c, where b and c are two constants at the old value nu, it will become b times x times nu times c plus b times nu times x times c. So those terms are all linear because every summand in the expression, they at most involve one variable. So if we go back to the termination probability analysis, what does that mean? Which means that, okay, we start from the original equation, we do the linearization, then we obtain a linearized equation. So if we can demonstrate that visually, so here's a control flow graph for the original equation for the recursive procedure x. We can also do this visualization for the linearized equation. As you can see that we have one more pass from the function entry to function exit. But then from every entry to exit path, there is at most one procedure call where I mark in yellow. Here is something. It seems like the Newtonian program analysis in trying to do some exploration. For example, for the left path, it performs exploration for the first call, and for the second call, you reuse the previous solution nu as a procedure summary. And for the second pass, it will reuse nu for the first call, but then perform exploration on the second call. And finally, it will combine the results using the combine operation. Okay, so if we plug in the whole stuff back into the program analysis pipeline, so this amounts to we can, again, interpret all the algebraic operations by their interpretation, basically numerical interpretation, obtain a linear equation, which can be solved very easily, and they can obtain the iteration scheme for Newton's method to solve termination probability analysis. So far, we just talked about something that can already be done by the framework developed by SPLASH'24 already in 2008. So the whole framework is Newtonian. It can handle probabilistic programs. It looks very promising. Indeed, Newtonian program analysis is suitable in this case because due to the quantitative nature of probabilistic programs. But there's one key missing part for the whole story is that we only consider one combined operation, but in practice, probabilistic program can have multiple kinds of branching, like probabilistic ones, non-deterministic ones, and conditional ones. So the actual work we did in our paper is to tackle this key challenge. So how to extend Newtonian program analysis to support multiple combined operation. So I'm not going to go into the technical details of the whole pipeline of our work, but I will just revisit the whole pipeline to see where we need to do some change to support this kind of multiple branching stuff. So the first thing is that we need to change the intermediate representation, which is control flow graphs here, because here on the control flow graph, like for the branching or confluence nodes, they are interpreted by the combine operation. But now if we want to support multiple combined operation, we need to first kind of distinguish these different kinds of branching in the graph already. So our solution is to use control flow hypergraph. where the hypergraph means like a normal direct graph where each hyperedge can have one source node but multiple destination nodes. To see why we need that, consider this kind of non-deterministic program, which will first make a non-deterministic choice, and then in one branch, it assigns x with value 1 or 2 with probability 1/2, and in the other branch, it also assigns randomly to variable x with value of 3 or 4 with probability 1/2. So we can represent the control flow of this program as a control flow hypergraph in the sense that we have these yellow edges, which are just hyper edges. It has one source node and two destination nodes to represent such kind of control flow. The good thing is that when we're composing hyper edges together, we get hyper paths, which are basically some tree structure as a generalization of program execution paths. The good thing is that we can distinguish like an execution paths from different distribution. For example, here we have two non-deterministic choices, so we can finally in the semantic we have two different distributions. So once we have these control flow hypergraphs, we can then think about, okay, how can we represent this kind of control flow hypergraphs as a data flow equation algebraically? So the idea is that we can represent this control flow hypergraph as a tree expression. The high-level idea is we can unfold the control flow graph from the entry node to the exit node. Then we can obtain like a tree-like structure where every root leaf path stands for an execution path in the original control flow hypergraph. Then we can also turn it into a finite expression, like a tree expression. We can raise the expression outside in. The first is a non-deterministic choice, followed by two branches. One branch will have, both branches have a probabilistic choice, which assign to program a variable x with different values. Then we can use as a generalization of semi-rings, which we call Markov algebras, which is basically semi-rings plus multiple combined operations as the as a semantic model for our program analysis. So basically, to have like a semi-ring structure for the abstract semantics, then we have different combined operations. This circular plus with a subscript, it stands for probabilistic and conditional branching, and the square cap, it stands for non-deterministic branching. So after we turn the whole control flow hypergraph into an algebraic equation, then the next step is to solve the equation by Newton's method. So we just follow the idea of Newtonian program analysis. What we need to do is just to define some syntactic linearization rule for the new operations we introduced in Markov algebra and prove they are sound. And in this case, we can do very similar to this equation we have seen earlier in the presentation. And also visually, I would like to stress it's similar to the visualization of control flow graphs. Now we have these tree-like structures. Originally, we have this tree on the left. On the right path, we have two consecutive procedure calls. And after the linearization, we obtain a more complex tree. But then on every root to leaf path, there's at the most one procedure call, which makes all of the program linear. So finally, then after we obtain the linearized equation, we need to solve them. But unfortunately, currently we don't have a generic way to do that because so it requires each program analysis to provide a strategy for solving these linearized equations. We did some case studies on 4 different program analyses. Here just show the evaluation results for 2 of such case studies, one for termination probability analysis, and the other for moment of reward analysis. We compare our efficiency against clean iteration on some synthesized benchmark programs, and the point in the lower right triangular region means the benchmarks of our method can be faster than clean iteration. So to summarize, the key takeaway is that in this work, we extend Newtonian program analysis to support multiple combined operations so as to enable analysis of programs with probabilistic, non-deterministic, and conditional branching. And you can find more in the paper about how can we support loops and or unstructured control flows, how do we prove the soundness, and also more case studies. Especially there's one very interesting one about invariant analysis. And thank you, and thanks for your attention, and the question are welcome.
We have time for one quick question. Maybe you want to set up while we take the questions.
Hi, very nice talk. So I was wondering, does this method also extend to programs with continuous probability distributions? Or is it only discrete branching that is?
Yeah, that's a good question. So it actually works with continuous probability distributions. So actually, if you can have an instantiation of the Markov algebra that can work with continuous distributions, then it seems to be fine. And in one of our case studies, we actually support continuous distributions.
All right. Thanks. Very nice work.
Right. Thank you again. Okay, so next talk is about proving non-termination, given by Julian.
Are we on? Awesome. Good afternoon. My name is Julien Van Egg. Today I'm going to present our work about non-termination proving at scale, which is joint work with Azalea Rad and Peter O'Hearn. So why do we care about non-termination bugs? First of all, we all know that termination is an undecidable property. It's not possible to prove termination for every program in a general case. And not only that, but termination bugs in real programs, they're very pernicious. They're really hard to see because when you have a program that actually do not terminate, typically that program is not going to respond. And it's possible that you have, for example, a server where all of a sudden is not responding anymore to the request from the clients, and you're not going to see any crash. And that can lead to real problems, real security issues such as denial of service attacks. On top of that, in the last 20 plus years, we found more than 1,000 non-termination bugs were identified publicly and reported in the MITRE CVE database. And as we can see, the trend of those bugs is going up. And it affects all languages that are Turing complete. That's the case for C, C++, Java, but also for JavaScript, Rust, Go, and every other memory safe language. So here we're talking about really a property that's going beyond memory safety. So let's talk about what we know already, the past, the correctness, and the over approximation techniques that people have been using mostly to prove termination in the past. Obviously, correctness, as you all know, is proving the absence of bug. So for example, if you have a piece of code C and you start in a pre-state satisfying the precondition P, and you know that this piece of code terminates, then that will lead to a post-state that satisfies the post-condition. Proving this in the over-approximate setting will be guaranteeing you the absence of bug. However, you may have false positive because you may analyze spurious behaviors of the program. On the other hand, using incorrectness reasoning and under-approximation is meant to prove the presence of bugs. So it may be that you found a bunch of bugs, but also you will have no false positive by construction. So it's really useful to be able to put this in front of developers because those developers are really sensitive to noise. And as soon as you actually put a static analysis tool in front of them that has noise, then they're not going to like you. They're going to disable the tool. So it was very important to us to focus on a methodology that was no false positive by construction at the expense of false negatives. Just a few reminders about incorrectness logic. Incorrectness logic is a logic that was created by Peter O'Hearn, published at POPL 2020. And the semantic triples for incorrectness logic are as such. It's using the square bracket instead of the curly brackets as in whole logic. And on top of that has a tag, epsilon, in the post condition that can tag whether you are analyzing a normal execution, an execution that has no error, or an erroneous execution that is leading to an error state. For example, if you want to analyze this fragment of code x equal y, and you know that y equal v, then you know that in the post condition, x is equal to y is equal to v. On the other hand, if you hit an error in a piece of code that you're analyzing and you started to execute this error in precondition P, you know that you're going to lead to an error state that also satisfies P. So one of the first contribution of the paper is that the realization that there are two kinds of under-approximation. The first is called forward under-approximation, and the other backwards under-approximation. And it turns out that those two under-approximation styles are equivalent. You can differentiate those two by their characterization lemma. At the top, you are quantifying over the post states. So for all S in the post, satisfying the post condition Q, there exists a state S prime in P, such as S prime is linked to S by executing C, starting in P. So really, this corresponds to the existence of a path. On the other hand, you can also quantify on the pre-states and require that there is at least a post-state S prime in Q, such as S and S prime are linked by executing C. This is also known as a Lisbon triple. So in under-approximate reasoning, you can use a bunch of standard rules. For example, you can use sequential composition on the right-hand side. If you have a piece of code C1 that starts in a precondition satisfying P and leads to a post-condition state satisfying R, and then you have another piece of code C2 that starts in a pre-state that satisfies R and leads to a post-state satisfying Q, you can do a sequential composition of C1 and C2 to build C1, then C2 that goes from P to Q. In incorrectness logic on top of that, you can use something called short-circuiting, where if you know that C1 starting in P goes to an error state satisfying Q, you know that any sequential composition, C1 compose C2, say, will also lead to a error post-condition Q. You can also model branch in incorrectness logic. For example, you can have a choice operator where you can decide whether you want to actually go down the path of an if or the path of an else. And this is called path dropping. It's really useful to be able to scale to very large programs because you can focus on specific paths that you care about. In incorrectness logic, you also have rules to handle loops. For example, you may unroll many times a given loop, going from P to Q, or you may unroll 0 times, say if you never enter the loop, where P and executing C 0 times still lead to post-condition satisfying P. And that's really powerful as well because you can do a bounded loop analysis, so you can do basically K-bounded loop analysis where you can go down the path of a loop until a certain bound, and that avoids you to really get into infinite path of a given loop execution. These are great, but this doesn't handle termination or non-termination. In fact, incorrectness logic only handles finite traces. But one of the realizations is that while termination is a correctness property, non-termination is an incorrectness property. Indeed, if you look at the piece of code at the top, in order to know that if ren skip else x equal 1 terminates, you need to go down every path, and you need to know that the if part is going to terminate, as well as the else part is going to terminate, which is the case in our small program fragment here. If you want to prove non-termination on a program, for example, the below code, if ren skip, do nothing, else, while true skip, diverge, then you only need to prove that one path of the program is actually non-terminating, which is why non-termination is inherently an incorrectness question. So we built a new logic based on incorrectness logic called UNTER, and UNTER stands for non-termination, under-approximate non-termination logic, where we combined the incorrectness logic rules with the divergence rules to be able to analyze very large programs that have potentially infinite loops, cyclic go-tos, et cetera, et cetera. So how does that look like? We introduced those new triples called divergence triples. And the way they read is that if you execute a piece of code C that starts in a pre-state satisfying P, well, then C diverge, right? So if you execute C in a precondition P, then C diverge, or C as a divergent trace starting from P. That, for example, represent, graphically speaking, a trace that never terminates, that goes from S to S1 to S2, and that goes infinitely like that. We have a bunch of divergence proof rules in our logic. For example, conditionals, where you start, if you assume that P and B C1 diverge, if C1 diverge starting in P and B precondition, then if B C1 else C2 diverge starting in P. Similarly, if you know that C2 diverge when you start from a pre-state satisfying P and not B, then if B C1 else C2 diverge when it starts in P. Similarly, those divergence rules handle loops just fine. If you have a piece of code C that goes from P and B to P and B, then you know that if you put that piece of code C into a loop while B, then while B C, starting in a pre-state, satisfying P and B diverge. This is what we call a lasso property. You can imagine like a very large state space in a graph. And in fact, if imagine a cowboy lasso feature in that state space where you basically come back on an existing state that you've seen before, and you only need to analyze a finite prefix of a trace to determine that this particular path is not going to terminate. We have another while divergence rule where if you have a piece of code C that starts, if starting in a pre-state satisfying P and B diverge, then you know that while B C will diverge if it starts in P. We can also handle sequential composition just fine. If you have a piece of code C1 that goes from P to Q, and another piece of code C2 that goes from Q and diverge, then you know that the sequential composition on C1 and C2 diverge. Similarly, you can have short-circuiting in divergence analysis, where if you have a piece of code C1 that goes starting in P diverge, then you know that the sequence of C1 and C2 will diverge when starting in P. It's great. It's beautiful. We have a soundness and completeness result for this logic. But not only that, we built a tool. We actually implemented this in the infer framework from Meta, and particularly we extended the pulse checker to be able to find non-termination bugs. We've also combined the Hunter logic with separation logic for compositional analysis. And this tool is open source. You can check it out at GitHub, on github.com. And we found a number of different divergence bugs in real projects. We've got the reusable badge at OOPSLA. And we're working with the Meta folks to extend the tool and integrate possibly. Our results, we found a bunch of real bugs in a bunch of real programs. As far as we know, we are the first tool that can handle very large programs for non-termination analysis. I want to attract your attention not only on the bugs found, but also how fast that tool actually is. In order to analyze OpenSSL, we need a minute and a half to analyze 800,000 lines of code, thanks to the path dropping and the k-bounded analysis that we've implemented. A few examples of bugs we found, for example, in OpenSSL. If you look at the OCSP responder implementation, you see loops like that, where the user actually fully controls what comes on this I/O, and the loop will never terminate if the user data keeps coming in. There are only two loop breaking logic at line 6 and line 9, but this only depends on whether you receive nothing or whether that value actually didn't contain a colon character, which is fully user controlled. We've also found a bunch of bugs in the crypto PP C++ cryptographic engine. For example, that engine actually wraps the malloc calls. And what it does is that as we all know, when malloc fails, it will return a null pointer. So if you keep trying, you will maybe eventually get some properly allocated memory. However, the crypto PP package do not enforce an upper bound on how many times you're going to retry. You can fix this bug very easily by introducing a number of maximum count. Thank you very much, and I'll take your questions.
Any questions?
Hey, very nice, very elegant work. So looking at your rule for while loops, the one that says that you start from true and you end with true, and so imagine that I am in a concurrent library and I have something like a spin lock implementation which would satisfy this rule. That would probably be a false positive because it assumes that there is concurrently someone who will eventually going to unlock it. You will probably need some fairness for that. So can you comment on that? So what would you do about that?
Great point. We do not handle concurrency in this logic right now. However, one could imagine an extension of the logic in handling concurrency.
Hi, very nice talk. I have a question. The proving non-termination paper that I knew before this one was from POPL 2008 by Tom Hensinger and Rupak Majumdar and so on. How they did not do logic, so it's clearly something new is going on. But in terms of sort of expressive power or something, what's the relationship between their work and your work?
So, because we use separation logic, we're compositional.
Right.
Like no previous work combines separation logic with non-termination, as far as we know. So this allows us to actually handle real programs that are extremely large. We're talking million lines of code program. Right. Every other tool that we've tried was not able to handle things that didn't have a main function. So that's the first point. Of course, the logic allows us to be more systematic about it, so we do not need any special encoding. As long as we have, the implementation follows the program logic, we don't need to reason about arithmetic or anything like that. And I know, for example, POPL Gupta, POPL 08, I believe, were all about recurring sets, encoding in arithmetic.
Yeah.
So it's related work, certainly, but we brought it to the next level.
Okay, so the compositionality is very important in your work.
Absolutely.
Yeah, very good, thank you.
Hi, very nice talk. So my question is about lassos. So to the best of my knowledge, most of these works on non-termination that search for a non-terminating lasso find a periodic non-terminating lasso. So the cycle is always of the same length. But it seems to me that you're able to find a witness which does not need to be periodic. So it's also able to detect aperiodic lassos.
Right, so we able, first of all, if you look at the paper, our rule is not that we find the same state, is that we find a state that is a substate of a state we've already seen. That's a slight difference. Also, we only need to find a lasso in one path, right? Not necessarily, not every path, in order to have a non-terminating program, not every path have to diverge, only one path. That's a big difference between previous work and what we've done.
All right.
Am I answering your question?
Yeah. Okay. Thanks.
So I have two questions. One is, I think what you just said. So you're not just doing under-approximated reasoning. You're doing a combination of under and over approximation. Because you mentioned you want a sub-state to be reachable, not the entire state to be reachable, right? When you look for lassos.
So we actually only do under approximation, but by sub-state, I mean that not every variable of the state have to be taken into account. In particular, only the variables appearing in control predicates should be are sufficient to induce non-termination.
So you're just projecting out some things, and then you do incorrectness reasoning. Like you do, okay.
That's right.
And so the other part I understand, like, I got the compositional part, like how it all pieces together, but I missed the atom part. Like, what is the initial step that triggers the non-termination analysis? Like, what is step 0? Like, I see how everything propagates beautifully, but like, how do you find the first clue of non-termination?
Right. So it all boils down to this lasso property here, right? So if you, for example, execute a piece of code that you see is not making any progress, it's not necessarily a divergence bug in itself. That piece of code needs to be part of a recurring execution. So whether that's a recursive function, or it's a cyclic go-to loop, or it's a loop that itself is not making any progress, that is necessary to have a real divergence bug. So, for example, if you, the most basic example, if you do go to yourself, right, that would lead to a divergence bug.
Hi, thank you for the nice talk. I'm a bit puzzled by the second while loop rule for the divergence. Why don't you need that the initial state satisfies B? Because otherwise I couldn't skip the while loop in total, right?
That's right. Well, so if it's not actually satisfying B, you're never going to enter the loop, so there's no divergence.
Yeah, but you have to, right?
Well,
for the second rule down there, I mean, it says, yeah, if you satisfy P.
Say you remove B in P and B, if you have C diverge starting in P, then nothing guarantees you that you will enter the loop.
Yes.
So you need this extra piece of information to know that this loop will be entered, and therefore there will be a recurring state leading to a divergence.
Yeah, but here you say you don't need it, right?
I'm sorry?
Here you say you don't need it, or I think I'm a bit puzzled.
Yeah.
Thank you.
Here's another way to think about it. You can actually infer that the entire program will diverge. So if this particular divergent piece of code into the bigger program context, then you can prove that the bigger program will diverge, not just that small piece of code.
Hello, I have a small question. How do
Sorry, I think we need to continue here, so
Okay.
let's
Thank you very much.
take remaining questions
take
in the break.
Questions in the hallway.
Thanks again. Okay, so the last talk of this session is about quantum control programs.
Hi everyone, I'm Charles, and I'm really excited today to share with you the research that we've done on some of the fundamental challenges of programming a quantum computer. This is joint work with my collaborators Aggie and Mike at MIT. So to start, what is a quantum computer and why do we want to build one? Well, in short, a quantum computer is a device that exploits the properties of quantum information to solve problems faster than any classical computer can. Specifically, quantum algorithms are known that can deliver asymptotic advantages for a variety of tasks, ranging from factoring numbers and breaking cryptography, to solving large systems of linear equations, as you might find in machine learning or optimization, as well as physical simulation for chemistry or physics. And the way these algorithms achieve that advantage is by exploiting quantum information. Whereas a classical bit can exist either as the state 0 or 1, a quantum bit or qubit can exist as 0 and 1 simultaneously, in what's called a superposition. So on the slide here, I presented the math for a superposition. It's a linear combination of these zeros and ones. You'll see these funky looking angle brackets, which are called kets. Physicists use kets to denote quantum information. So whenever you see something inside a ket in this talk, just think that's being encoded inside the qubits of some quantum computer. There are also these coefficients in front of them, which are called amplitudes. They kind of denote how much 0 or 1 there exists inside the superposition. And one thing that it tells you is what actually happens when you take Schrödinger's cat, which is both alive and dead at the same time, and open the box. You'll get a classical outcome, in this case, either 0 or 1 with some probability. Okay, so this process is called measurement, and it is probabilistic. The probability of seeing 0 or 1 comes from, it turns out, the square of the norms of the amplitudes. So the amplitudes are actually complex numbers here. Unlike classical probabilities, which are real, amplitudes can have signs, which in this case is called phase, like the phase of a wave. I won't get too much into the depths here of what that means, but the ability for quantum information to be in superposition and have these signs and phases is really important for algorithms to get that advantage. These algorithms have received renewed attention over the last few years because in the last 2 years, we've actually made huge strides in building the hardware that will be necessary to execute these algorithms on real quantum computers at scale. But the question that I want to examine today is not specifically how we build the hardware, but rather how we're going to program these computers. So imagine that you're a developer who's interested in implementing Shor's algorithm for factoring large numbers. Okay, so you can open the paper, and you'll find a mathematical description of how the algorithm works. It has some notation and some English text, basically. And I'll go ahead and summarize for you what's going on here. This is actually the computational bottleneck step of Shor's algorithm, which is doing modular exponentiation. We have integers a and x, and we want to compute x to the a mod n. The way the algorithm does this is by repeatedly iterating a modular multiplication by x mod n. Now, as a programmer, whenever I see a pattern like iteration, I tend to reach for a for loop when it comes to implementing this operation as a program. And indeed, if this were a classical algorithm on a classical computer, you could probably do this in about 1 line of Python code. Okay? But how hard do you think it is to implement this part of Shor's algorithm in a state-of-the-art quantum programming framework? Did you expect it to be this hard? Okay, so this is the implementation of that part of Shor's algorithm in Microsoft's Q# quantum programming framework. The text is extremely small. Let's blow it up and see what's going on. And when we do that, we'll notice that the reason the program is actually so complex is because the abstractions that the program is manipulating are individual logic gates. For example, there's that X gate, if you look in there, that is being controlled on the values of individual bits. So there are some other examples of algorithms that are specified like this. Okay, it's in the form of a quantum circuit, a sequence of individual logic gates acting on individual qubits. That is the standard for how scientists communicate quantum algorithms and effectively program quantum computers today. Okay, so on the slide here, I present some other examples of circuits from algorithms for physical simulation. You can see every line in that circuit is a qubit. Every line from the left to the right to the page, every box or every dot is some logic gate that's going on. So I don't know about you, but I would hate to be a programmer who is in charge of implementing a program like this one, making a mistake somewhere, and then having to figure out where I went wrong. Okay? So the question then that a lot of programming languages researchers have asked is, can we build higher level quantum programming languages that feature cool abstractions that let us get around this problem? There's been a lot of progress on this front in this community over the last few years. What we've actually been able to do is to come up with this next generation of quantum programming languages that introduces abstractions such as if statements and for loops that you can actually use to express control flow rather than hardware. Okay? This is really great, but the existing languages still have a bit of a problem, which is that if you compare them to essentially any classical programming language, their capabilities pale in comparison. Right? Control flow is kind of widely considered a solved problem in classical programming. Why is it so hard to implement such a fundamental idea on a quantum computer, and how do we get across this expressivity gap? Well, we answer that question in this work. And to give you a hint, it has to do with the way that we reason about and compile the quantum programming languages. All of the languages that I just showed you have the property that they take a high-level control flow construct, like an if statement, and compile it pretty much directly to a logic gate or a sequence of logic gates in a circuit. So this nested if statement just turns into a single logic gate that's controlled on 2 qubits, a very hardware-level translation. But that's not how classical programming languages work, right? They tend to assume the existence of a CPU with a program counter and a conditional jump instruction. And this instruction forms the compilation target of basically every control flow construct that we know and love. It'd be really cool to just be able to do this on a quantum computer. But what we show in this work is that that's not going to work. We show that a quantum computer fundamentally does not support the conventional notion of a conditional jump. We show, however, that they are going to support a reinvented concept of a conditional jump that satisfies additional properties. We'll end up formalizing all of this through a complete specification of the forms of control flow that you can actually realize on a quantum computer, and an instruction set that enables us for the first time to implement control flow and pave a way forward towards extending quantum programming languages. So let's get right into that first claim. Okay, I want to be more concrete about what it means to not support a conditional jump. So what even is control flow? Well, here's a very small example of a program. Here you can see it's got an if statement and it's doing something inside each one of the branches. Okay? Now, I'm going to feed this program an input, and I'm going to expect it to give me some output. Okay? And so I have some values of x and y and some corresponding output values of x and y. And the way that the program will execute is that it's got this program counter register, which starts on line 0, and then in this case, due to the value of x, skips to line 3, and then eventually goes to line 5, and the program halts and gives the right answer. Okay? That's how classical control flow works. Nothing interesting there. But of course, on a quantum computer, the whole point is that we want everything to be in superposition. Okay? So now instead of just feeding in a single value of x and y, we're going to feed in a superposition of x and y. Remember that ket notation from before. All we're saying here is that we've got a whole bunch of qubits that are encoding states of x and y that are 0, 3, and 3, 0 at the same time. There is still that amplitude and that minus sign, We're not going to focus too much on exactly what their values are, but they have to be there, right? They kind of characterize what a superposition is. All right, so how can we execute this program by the analogy of what we did before? Well, we're going to start with line 0, and then something very interesting happens, because x is now a superposition of 0 and 3, which means that conceptually we're executing 2 lines of the program at the same time. We have a superposition of the program counter, okay? So this is all fine and good. It's a reasonable specification for how to do control flow and superposition. We're going to need to compile it down to the explicit instructions that actually manipulate the program counter to get that step to work, to take the program counter and put it into superposition. And it is, in fact, this instruction that will end up showing cannot be physically realized on a quantum computer. So that's the formal statement that I want to make. Let's get into a little bit about what the proof of this claim looks like. I'll do that by showing you a couple of previously proposed or conceived approaches for how to realize this form of control flow on a quantum computer and why they do not work. One of the first things that you might think to try is, well, I told you about this measurement operation, right? Why don't we measure the value of the variable, get a classical answer, and then use that to perform the control flow? The problem is that, supposing that we start with some data in superposition for the variable x here, measurement will cause it to become a classical state with some probability. So maybe it just becomes 0. And then, of course, we can execute the rest of the program and we'll get some answer. But as you can see, the program has just become classical at this point. Right? There is no superposition anymore. The algorithm cannot possibly get any advantage over a classical algorithm if we're just performing measurements willy-nilly. In general, doing this is going to cause a quantum algorithm to completely lose its computational advantage. Based on this observation, what we have to realize is that a quantum computer fundamentally restricts the kind of operations you can perform on the data inside the machine without collapsing its superposition. Mathematically, the operations you can perform on quantum data while preserving its superposition are called unitary operators. Right? What is a unitary operator? Well, it has a mathematical definition. We could get into that in the paper. But the only thing that we actually really need to know about a unitary operator is that it is an invertible mathematical function. And what that actually means is that if you think of the semantics of a quantum program, or any line or any instruction in a quantum program, the denotation of that program or instruction has to be a unitary operator that is reversible. You should be able to conceptually go either from the input to the output, or if I give you the output, you should be able to tell me exactly what the input was. There's this one-to-one relationship between them. So that will actually be the first property that we need to enforce. The semantics of every statement or every instruction in how we program a quantum computer has to be reversible. There's another property. Let me tell you about that one next. And to do that, I'll dig up this state from a few slides ago where we had the superposition of the program counter. Let me blow up that state. And you'll notice that I have hidden the 1 over square root of 2 and stuff. It's not so important here. The important thing to note about this state is that, well, it's telling us about the state of the program counter and the data registers x and y. Now, when we program a computer, we generally want to just work with the data. We want to produce an answer that is just the data registers. Typically, we'll execute the program, get some final program counter, and then disregard that program counter and just return the data. Quantum algorithms want to do the same thing. They want to be able to just talk about that data and return it. But how do we actually do that? We kind of have to explicitly get rid of this program counter. This is kind of a counterintuitive thing to think about because classically, well, of course, you just delete the data. You don't care about it. But how do we delete quantum information? Is that even a thing that we can do? Well, one thing we can try to do is to measure it, right? Measurement will allow us to turn quantum data into classical, but something very bad happens if we try to measure the program counter here. A phenomenon called quantum entanglement kicks in. You may have heard of this concept. It states that in certain quantum states, measuring a part of the quantum state will collapse the superposition of not only the part that you measured, but the entire state. So if you try to get rid of the program counter here by measuring it, or even via more other underhanded techniques like throwing it out or pretending that it never existed or whatever, quantum mechanics will dictate that the result is that the superposition of x and y, the data you care about, will also collapse. If you prefer a more mathematical presentation, you can think of entanglement as saying, well, I have this quantum state that has the program counter and some data registers. Can I write that quantum state as a tensor product of just the program counter and then a bunch of data registers? An entangled state is one for which this is not possible. We're going to want a state for which this is possible, which is called a separable state. Okay? That will be the second criterion that we need. We need a state that ends up being separable so that we can get the data out and leave behind the control flow. All right, so we basically now have all of the ingredients to show why we can't do a conditional jump on a quantum computer. If we look at the semantics of a program that uses conditional jumps, or jumps in general, we can ask the question of, is the way that the state of the machine evolving through time as we execute these instructions, is that evolution a reversible process? And the answer is no, it is not. You can come up pretty easily with examples where you have two distinct initial states, and then you execute one line in your program and they go to the same final state, which indicates that in fact this is not a reversible process. You might be thinking at this point, surely there are some workarounds that you can do to overcome this problem, right? Prior work, for example, has proposed a very simple solution of just writing down the old values of the program counter, right? So if you see, if we maintain this history of the old program counter being either 2 or 4 in this case, then you'll see that given the distinct inputs, they'll always go to distinct outputs. So now we have a function that is reversible. But is it going to satisfy that separability property? Well, to see why it doesn't satisfy the property, let's look at this, which is the state that we want, right? We want the output state to have the x and y's in this way. And if we apply that trick of writing down the histories, this is the state that we actually have. I put the histories there in orange. What kind of state is this one? It is an entangled state. You can tell that it's an entangled state because if you look at the value of each branch of the superposition, on the branch where I know that PC prime equals 4, I know that x equals 0. And on the other branch where PC prime equals 2, I know that x equals 3. According to quantum mechanics, this means that if I measure one of those variables, I will also learn information about the other one, thereby collapsing its superposition. The result will be that no matter what I do, I can't get the data out of this computation without losing its superposition and destroying the advantage of the quantum algorithm. So that was, in a nutshell, the proof idea for our claim that you can't do a conditional jump on a quantum computer. Of course, there's a formal statement and proof in our paper. But what I want to move to now is some implications of this idea. So back in the 1930s, we figured out as computer scientists how to stop programming in terms of hardware level abstractions, like zeros and ones and noughts, and move to higher level abstractions like the lambda calculus. This has had implications for programming languages and computer science. It would be really great to be able to work with quantum computations like this too, to be able to stop talking about superpositions of zeros and ones and instead take arbitrary objects and give them the ability to exist in superposition. I wish I came up with this idea. In fact, I was beaten to it by this really great paper back in 2004, which proposed a lambda calculus where you can take the terms and put them in superposition. But this story has a bit of a sad ending, which is that the author of this paper never showed how to take this calculus and actually compile it to a real quantum computer. In this work, we prove why, which is that we show that these sorts of lambda calculi simply can't be physically realized. And the reason is the same as we've discussed before. The process of beta reducing a lambda term is not reversible, right? Identity function reduces to identity function. Identity applied to identity reduces to identity. Okay? This is fundamentally not going to work. So what our work really shows is that reversibility is a barrier towards programming a quantum computer. We view this as an organizing result that states that quantum programming languages aren't going to get better unless we radically rethink our abstractions. And I want to just give you a brief idea of how we might rethink these abstractions, okay? The problem that we encountered, right, is that sometimes we can be sitting at a line in a program, like line 5 here, and not know where we just came from, right? That's that reversibility problem. But what if we had a new instruction set where every instruction tells you where you just came from, where we made the targets of all jump instructions carry additional metadata that says, for example, in this case, if you're sitting on line 5, then this instruction, which you can pronounce as reverse jump to line 2 if x is not equal to 0, this instruction will tell you that if you're at this line and x is equal to 0, you must have just come from line 4. Or if x is non-zero, you must have just come from line 2. By doing this trick, you can essentially have a new instruction set that makes the semantics of every instruction reversible. Of course, there's a whole bunch of stuff that needs to go on behind the scenes to come up with a whole abstract machine that redefines jumps to make this happen. But the effect is that we can actually do this, right? We can actually come up with this reversible instruction set. The only thing that we need to do now is to also satisfy this separability property. And while the details are in the paper, I'll summarize it by saying that the key property we need to enforce here is just that while the program might manipulate the program counter however it wants in the middle of the program, by the very end, the program counter must be separable, not entangled with the data registers. And a simple way to do that is to just make sure that it's always equal to the same value on each branch of the superposition. In this example, we just say it's equal to 5 everywhere. The upshot of all this is that for the first time, we can now actually express control flow in a quantum algorithm without utilizing hardware-level logic gates, okay? Which is a very big improvement in our ability to program a quantum computer using high-level abstractions. There are a lot of open questions here. For example, how do we take this design and make it more practical in hardware terms? We don't know yet. We also don't yet know how to potentially generalize this idea to concepts that more resemble functional programming while taking into account the impossibility results we showed earlier. But we do believe that this is a first step towards more expressive languages and tools to teach, invent, and analyze quantum algorithms. To summarize, I've shown you that in this work that if we program a quantum computer the way we program a classical computer, using the same sorts of abstractions, we'll end up turning that quantum computer into a classical computer, something that can't achieve any of this quantum computational advantage. But fortunately, we can build new abstractions that let us both harness this computational power and our wisdom in classical programming abstractions. That's the end of my talk. One last thing, I'm on the faculty job market this year, so if you think this research is cool and your department is hiring, I would love to chat. Thank you.
Thank you, Charles. Any questions? I'm sure Jens has a question.
But let me begin by saying, so people remember that Dijkstra had this paper called "Goto Considered Harmful" in 1972. What's less known is that in 1973, Clark had a follow-up that was called "That's Fine, We'll Just Use Come From," and which seems to me to be what you're doing, that you have to explicitly...
There's something very, very poetic and about the way that this reverse jump operator is similar to that come from operator. There are, of course, some formal differences, right? It is not a construct that arbitrarily transfers control, but rather a construct that says, transfer of control just happened. This construct is metadata that marks the way in which that transfer of control just happened.
Does it make programs long, to program in this style, does it add lines to the program, or does it just make the lines a little longer?
In our experience, the challenge is not really that the program gets longer, but rather you have to enforce additional properties on the correctness of your assembly code. Right? In classical assembly, if you have jump statements, the only thing you really need to worry about is that the target of your jump is a valid instruction. It's not like in the middle of an instruction or something like that. But now you have additional properties that say the target of a jump instruction must have the correct metadata that says, under this condition, you jump from there, and under another condition, you jump from somewhere else. That, in general, can be a little bit hard to write and to verify. And we've got some thoughts on how to make that process better, but it's still a work in progress.
Any last questions?
Hello, yep. The part about separability went by a bit fast for me, and I'm really surprised how you can achieve this. So if I understood right, I can jump anywhere that I want in the program as long as I have some final instruction at the end, like say line 99. And as long as we both end up there, we can jump any way we want. Is that correct?
That's the high-level correctness property, right? At the end of the program, like on, at instruction number 16,000, whatever is the end of the program counter, the line number for each branch of the program must be the same. It's achieving that property and making sure that every branch of the program achieves that property at the same time that is the difficult part. For example, you can imagine a loop that runs for a variable number of iterations depending on some value. And if it reaches the same line of the program, but at different moments in time, that's a problem. So in our paper, we discuss, why that's a problem and ways to overcome it.
Okay, yeah, thanks for that. That helps a lot. Could I just add padding to the shorter branches?
Yes, that is one of the things that you can do. Right.
Thanks again, Charles.
Thank you.
third static analysis session. The first presenter in this session is going to be Hao-Non Lee from UC Riverside with his colleagues Yu Hao, Yisu Zai, and Ziyun Chan. And the paper is called Enhancing Static Analysis for Practical Bug Detection and LLM Integrated Approach.
Okay, thank you for your introduction. Hi everyone, this is Hao-Non Lee from UC Riverside. So today I'm going to share about our recent work, basically using large language model to help static analysis for bug detection in practice. And actually this work is inspired by our experience in static analysis. We do fail for static analysis, especially when you try to use static analysis for, for bug detection in practice, you will face many real challenges. Actually, ChatGPT will also agree with us at this point. If you ask ChatGPT what kind of disadvantages of the static analysis, it will tell us the following disadvantages of the static analysis. And actually, I picked some points here to share with you guys. And the first biggest problem is false positive and negatives. And also, static analysis is also struggle with its high complexity and also scalability issue. And static analysis, many static analysis also typically has limited domain knowledge. So it motivates us to think about how to solve these challenges. And of course, just as our title indicates, our solution here is using large language model. Compared to static analysis, LLM is very smart, and it typically has lots of domain knowledge and heuristics. Sometimes you can rely on LLM to give you some smart summary for kind of complicated code structure that static analysis may struggle with. But however, on the other hand, you can see LLM is also known for its unstable response, and they are typically has limited reasonability, especially when you try to reason on the code. So the problem here is, how can we really enhance static analysis by integrating large language model? So to answer this question, we researched on a specific static analysis tool called UBI tag. The UBI tag is designed to find use before initialization bug or UBI bugs in the Linux kernel. And the UBI is basically saying that variables may not be initialized during their use. For example, in the right figure shows there's variable v at line 2 and declare at line 2, and then there's an initializer for the variable v at line 4, and then v is used at line 5. So you can see at the line 5, the variable v may not be initialized because there's a constraint here. So before reaching the line 5, and here v is a UBI bug. The reason why we choose UBI tag as our target is because actually UBI tag shows many disadvantages of the static analysis. For example, it's false positive and negatives and so on. UBI tag actually has two design strategies. The first stage is static analysis. It's a static analysis is scalable one, but imprecise one. And then it's followed by a symbolic execution. It is very precise, but of course it's slow. So the first problem is the false positives. Actually, their static analysis can produce more than 95% false positives. So to handle this huge amount of false positives, UBI tag choose to employ symbolic execution to filter out these false positives by verifying the path. But however, symbolic execution is not perfect. It actually causes another biggest problem, the false negative. This is because symbolic execution can actually handle 60% of cases, and it will discard 40% cases, undecided cases, because of time or memory limitation. In other words, it may ignore 40% potential bugs. Let me give you a concrete example of the undecided cases. Here is the scanf. You can see at line 2 of the code, ABCD are declared at line 2, and in line 3 and 4, if you ask human to understand, It is pretty simple and straightforward. There's a scanf try to initialize ABCD, and more importantly, at line 4 there's a check to see whether the return value is greater or equal to 4. As we all know, this means when the scanf successfully initializes its first 4 parameters, then it will return a value greater or equal to 4. And in that sense, we can say at line 5, when ABCD be used, it is pretty safe. It is pretty safe. All the variables of ABCD are already successfully initialized. But however, this is very straightforward and easy for human, but this is not as easy for the static analysis. Our static analysis is essentially path insensitive, so it can only tell us scanf may not initialize by scanf, and it will report a UBI bug at line 5. And later, UBI tag will send this case to simple execution. But however, when simple execution goes into the details of the definition of the scanf, it will say when it want to infer the return value, it will say there's a variable num, and the num is essentially accumulated by the loop. So simple execution cannot really handle this case and ends up a timeout. So the only thing UBI tag will do is to directly discard this case. Of course, so this case scanf is clearly a false positive. The right thing you should do is discarding it. But actually, this strategy of the UBI tag directly discarding timeout cases will, is essentially, we will essentially have a risk of reject genuine bugs. So again, just as I mentioned, this case is pretty simple and straightforward for human to understand. So of course, we try to LM, we directly ask ChatGPT, are variables ABCD to be initialized before reaching the line 5? And actually, you can also scan this QR code to see the exact chat. And basically, ChatGPT will tell us here scanf is to is used to parse IP address, and by the time the call reaches the line 5, ABCD have been already initialized. So actually, the scanf is an example. It demonstrates that sometimes LLM can effectively analyze call logic that static analysis, our traditional static analysis, may struggle with. So based on these insights, we propose LLift using large language model to handle these challenging undecided cases. In a very high level, LLift takes these undecided cases from the UBI tag, and then we will ask LLM, are these variables initialized before they are used? And if LLM tells us must initialize, we will mark it as not a bug. Yeah, but of course, if you literally ask LLM, are these variables initialized before they are used, it won't work. This table is directly copied from our final evaluation. You can see we call this directly asking strategy a simple prompt, and you can see the simple prompt has pretty bad precision and recall compared to our final design. This is basically because bug detection. Our bug detection task is kind of complicated, and it essentially requires steps with kind of rigorous rules, just like what our static analysis do. And actually, LLM is unaware of them. So here, our solution here is actually, we don't LLM to think by itself. We will teach LLM, we will give the guidance to LLM for every steps and rules of the, of the bug detection. In other words, you can also understand it as we teach the LLM the mindset of the bug detection. But due to time limitation today, I'll show you guys all the details of our design. But I will give you some high-level design principles. I think that's the most important part of our work. And the first design principle here is, we call it is task decomposition, basically, because the bug detection is a very complicated task, so we'll break it into pieces that is more manageable for LM to think, to response. And the second one is, we call it post-conjoint guided path analysis. This is just as this shows. There is a variable v used at line 13. Line 13 is use of v, and the most critical part here is the line 12. There is a return value of the initializer, and to say the return value if the return value equal to 0. We call this return value equal to 0. We call this check as post-conjoint because it actually happens after the initializer. So we notice that we can actually take this post-conjoint into analysis of our initializer from the line 2 to 7. So basically, if we already know the return value must to become to 0, because otherwise there's no use, no UBI then the no UBI happens. So actually with this constraint, we can see very clearly the code can only reach the path 1, and we can directly prune the path 2. And this way, we can reduce a lot of unnecessary paths in our analysis. And the third design principle here is, we call it progressive prompt. Basically, in one word, the progressive prompt is to let LM itself decide what they want for function definitions. And you can see the whole process is iterative. LM can continuously ask for different function definitions until it feels it has enough information to give a conclusion for the function summary. So our workflow can be seen as a 3-step design. The first, we will take the bug report of the UBI tag and identify what is the initializer. And for example, in this case, the initializer for sure is scanf. And then we will extract the post constraint. And here, the post constraint is return value greater or equal to 4. And lastly, we will prompt LM to analyze the initializer with our post constraint guidance. So let's talk about our evaluation. Actually, we have 4 research questions in our paper, but today, again, due to the time limitation, I will focus on the first 2 parts of our evaluation. The first is precision and recall, and the second is some interesting result on other models than GPT-4. And our primary data set is, we call it random 300. Basically, it is coming from 300 cases from 53,000 undecided cases of UBI tag. And for the precision, the line, above the bottom line is coming from the random 300. We actually have 5 true positives with 50% precision. And for the recall, we don't really find any missed bugs in the random 300 cases. And furthermore, we also extend 300 to 1,000 to try to find more true positive bugs, and we do find 13. In total, 13 true positives and also 13 false positives. So again, the precision is still 50%. And actually, 4 of them are already confirmed as real bugs by the Linux community. And also, there are some interesting results. It's coming from for other models than GPT-4. A big disclaimer here is that actually this table is not coming from our paper. It's actually extended work after the paper submission. So you can see Airlift, our work can still perform very good on most other models. More interestingly is that even for open source models, for Llama, they still show a very useful and promising result, but just there are 2 negatives, or in other words, they have a much higher false positives. So, well, I'm super fast. So in summary, we present Airlift today. It's the first work to show how to use LM to improve static analysis in practice. And secondly, Airlift also introduces some new design strategies, post-test constraint guided path analysis and the progressive prompt. We believe this kind of design strategies can also help future studies in this area. And lastly, we test Airlift on real-world code bases, and we also achieve a very good precision and recall, and we also find 13 new true positives. And by the way, I will have a poster later today, and welcome to discuss with me later, and also you are welcome to give me some questions. Yeah, thank you for listening.
We have time for a few questions. Can you come up to the microphone, please?
Hello, thanks for the great talk. I have maybe a silly question, but I'm just wondering, so you wrote some rules in the prompts. I'm just wondering, couldn't you synthesize those rules in the static analysis part to improve the accuracy of that?
You mean use these rules in a traditional static analysis?
Yeah.
For example, yeah. For example, for our post-constraint guided path analysis design, literally you can also design in a static analysis way. Yeah, of course you can. And I believe if you really implement it with kind of a much more complicated work, you can also see the improvement.
Very nice talk. I'm Chenpeng Wang from Purdue University, and we also work on the similar directions as yours. I think the interaction between the symbolic analysis and the ALM is very interesting, but my current concern is that whether the performance of your evaluation actually depends on the precision of the symbolic analysis. For example, if many false positives are caused by the path insensitivity, and according to my experience, LLM cannot really filter such superior paths just by reasoning the path condition without using any kind of solver.
Actually, I feel like actually, you can see just this slide. Oops. Yeah, these slides. These slides, our post-conjoint guided path analysis. We do feel like for many cases in practice in the Linux kernel, we don't have a formal solver for the conjoint, for the post-conjoint. But actually, for most times, for this kind of return value, or you can say return value check, this kind of return value typically they will return an integer or return an error code in the Linux kernel. So in this case, it's quite simple to infer and the prune path.
So basically, the original symbolic analysis can really report this bug, right, as a false positive, and LLM can filter it.
Yeah, if this case is really as simple as this form, but again, for many more complicated code, just as the scanf case, simplification can do nothing with it.
Okay, because according to my experience, I do some experiment upon Julia test, even in some simple programs such as Julia test. If we detect divide by 0 or non-pointer dereference, the branch condition can be equal to 0 or not equal to 0, equal to null, not equal to null. I think the LLM alone will hallucinate when you just give the branch condition. So basically, I think the future extension could be ask the model to synthesize some script program and just find such on-site call.
Yes,
so I think it can mitigate some hallucination in this process.
Yes, for sure. But all the design is based on is essentially inspired by our experience. In our case, in our scenario, we don't really meet so many like complicated conjoint like what you're saying. But I also agree with that is definitely necessary if you want to figure out something like divided by 0 or non-pointer reference. Yeah.
Okay. Thank you for your answer.
Okay, let's thank the speaker again.
Okay, thank you.
Okay, our third talk will be semantic type-guided bug finding, and will be presented by Kay Wu.
Can you hear me? Nice. Okay, good afternoon, everyone. Thank you all for coming to this talk. My name is Wu Ke, and I'm a member of the PL lab at Johns Hopkins, led by Dr. Scott Smith. I'm excited to talk to you about our lab's work, semantic type-guided bug finding. Anyone here is a fan of static type checking? I really hope you are, because otherwise you probably came to the wrong talk. So let's talk a bit about static type checking. A common theme is that they almost inevitably rely on type systems. Unfortunately, it is impossible for a type system to be sound, complete, and decidable at the same time, so a trade-off must be made. Many practical type systems today are sound and decidable, but sacrificing completeness leads to good programs being rejected, limiting the language's expressiveness. So naturally, as researchers, we started wondering, can we do something else instead? More specifically, can we make a type checker without relying on traditional type systems? And building upon that foundation, can we also make the checker both sound and complete? That is to say, can we find all real type errors in a program and only those errors? So let's start with replacing type systems. Type systems are essentially a syntax-directed approach to typing. And if we want to do away with it, the natural alternative is a semantic-directed approach, which is aptly named semantic typing. And as its name suggests, semantic typing is where types are determined solely by the behaviors of an expression rather than any syntactic structure. In contrast to type systems, which use logical system as their foundation, semantic types use a semantic model to define the meaning of types. For example, in semantic typing, the type int includes any expression that evaluates to an integer. So to illustrate the difference, let's look at an example. In many type systems, a conditional is required to have the same type for both branches, and thus an expression like if true, then 0, else false would fail to type check in such a type system, but it will type check if we use the semantic definition of int. So this is a simple case, but it demonstrates how semantic typing has an edge over syntactic typing in terms of expressiveness. But there is a reason why semantic typing isn't widely used in type checking. Essentially, semantic typing is asked to run the code to a degree in order to perform type checking, which means if we want to use it statically, we must find a way to determine program behavior at compile time. But in general, the problem of compile time program behavior analysis can easily fall into the realm of undecidability. Fortunately, it turns out that although semantic type checking in general is not decidable, it is co-recursively enumerable, which means that if a type violation exists, it can be discovered in finite time. The downside to that, of course, is that if no type error exists, then any checking procedure might run forever. It is a clear limitation, but can be mitigated. I won't cover it in this talk, but I will be happy to discuss it afterwards. So with all that, our project proposes a co-recursively enumerable type checker based on the semantic typing notion, meaning just to reiterate, if semantic type error exists in a program, our tool will be able to prove it in finite time. The advantage here is clear. Semantic typing allows for a significant improvement in expressiveness. We have incorporated some rather complex type into the theory, but it's not really surprising since the whole appeal of semantic typing is higher expressiveness. But what is surprising is that by nature of our design, these complex types are expressed with relative ease in our theory, which we shall discuss in detail soon. So, yay. Okay, I will now offer a rough roadmap of the rest of this presentation. First, I'll start by defining a small untyped language, which will be the basis of subsequent discussions. And then I'll introduce two relations that will define how type checking works in our language. Next, I'll give an example of how more context types can be introduced to the language and talk about the actual implementation. We'll also briefly discuss the practicality and the performance evaluation of the implementation. And finally, I'll discuss some limitations of our work and what we hope to work on in the future. So, our core language is quite a standard functional language with integers, booleans, and function values. There are a few minor quirks about this language that's necessary for type checking. First, it allows for some basic type casing via pattern matching using the tilde symbol. It also has these pig primitives for integers and booleans, which are essentially non-deterministic pigs during evaluation. Apart from the above-mentioned features, the language has standard syntax and small-step operational semantics. One thing to note about the language is that although the language itself is untyped, we can verify whether an expression belongs to a certain type, i.e. whether the behavior matches the description of that type. Okay, now I'll give the model relation that defines what it means for an expression to have a type tau in our language. So here is the model definition. This is very similar to the standard inductive definition for basic types in logical relations. Intuitively, the cases for base types, int and bool in this case, state that an expression has type int or bool if it evaluates to an integer or boolean. And to type check a function, we actually need a full enumeration of the input space. For each value in the domain type, after applying the function to it, the application result must be a value in the codomain type. It's worth noting that for each clause, we're requiring all evaluations of the expressions to be a member of the specified type, which is to account for the baked-in non-determinism in our language. Another thing that may come off as a bit strange is that for function types, the definition doesn't really specify how the function should behave on arguments not in the domain type. That just showcases kind of a different philosophy of semantic typing. It only defines what's expected rather than what to exclude. But this particular model isn't readily implementable. For higher order function types, we cannot write an implementation that enumerates all possible function inputs. And as such, we need a more practical definition that can actually be implemented. So here's the second definition, TC, and TC defines how type checking actually works in our language. An expression has type tau if and only if the call to a checker function doesn't evaluate to error, and if it does evaluate to a value, the value has to be true. So what is this checker function? Below is the inductive definition for checker. The clauses for checking integers and booleans are quite intuitive. Again, it's simply type casing. The clause for functions is more interesting. We will formally define generator in a bit, but for now, you can think of it as a magical black box that will produce an arbitrary value from the given type. So with that in mind, you can see that it's doing something very similar to the more mathematical definition. To check a function type, you will generate an argument in the input type and then check whether the application result has the output type. So let's define generator. The generator's full definition is given below. Intuitively, the generators, when called, should give us an arbitrary value from the specified type. For integers and booleans, they're pretty intuitive. It's just their corresponding non-deterministic pick. The interesting clause is, again, for function types, there are two things that's happening in the generated function here. First, it will check whether the input is indeed in the specified input type. Then, after the check passes, you will produce an arbitrary value in the output type. So to sum up, here are some key observations about generator. First, it's responsible for introducing non-determinism to the checker whenever necessary. That is in the function type clause. And here's the definition for checker, just as a reminder. And also, according to this definition, generated function values will always produce outputs that are completely independent of their inputs. And that's bizarre, to say the least. So what that suggests is that our function generators, instead of trying to produce functions that have equivalent semantics to the real function in the type, they only aim to capture the behavior of these functions. That means for each run of a program containing a concrete function, if we replace that function with a generated function, there will be a set of specific choices for each non-deterministic pick that will result in the exact same program behavior. And that is the key to enumerating function inputs in the actual implementation. Overall, the key takeaway from this definition is the following. First, given a fixed type, both the checker and generator are just expressions in the core language. Second, checker is responsible for verifying the type of a value and will return false or error if the checking fails. And finally, generator is responsible for simulating the for all enumeration of a type. But before moving forward, you might be wondering, does that definition even make sense? Or more concretely, we want to prove that the more practical non-determinism-based checker is in fact equivalent to the model we first defined with respect to type checking, which can be summarized as the theorem shown on the slide. The proof can be found in our paper. The important takeaway is, with this theorem, we can safely use TC to realize semantic type checking in our implementation. But even with correctness proven, there's still the glaring question of what for if all this checker can handle is just simple types, then why not just use a type system? Well, as you might have observed by now, types are represented by a pair of functions in our language, a checker that verifies membership, and a generator that produces members in that type. This simple construction is actually very effective. We can express some really complex type with it. As an example, I'll demonstrate how we can extend our language with dependent function types. The syntax here is pretty standard. The model definition is provided as well, which again is pretty standard. It is similar to the normal function definition, with the only difference being that we need to substitute the argument into the output type when checking the application result. We also need to update the definition for TC to include dependent function types. The updated checker and generator for dependent function types are defined as such. As you can see, the checker mirrors the model definition really well. It generates a value from the input type and invokes the output type checker on the application after appropriate substitution. As for the generator, it's pretty much identical to how function types worked originally. The only difference, again, being the additional substitution. And that's it. Voila. Dependent function types added. Okay. So after all this talk about theory, let's talk about some actual concrete implementation. Our language and type checker are both implemented in OCaml. We allow selective type annotation in the implementation, which means the user gets to decide what expression to check and what not to. As will be demonstrated later, type checking is encoded as an error reachability problem in our implementation. Backend-wise, we use a concolic evaluator to look for reachable error states. Also, the actual implementation includes many more types in the core and the one extension we just presented. The full list of additional features are laid out on the slide. As you can see, we've managed to capture some pretty complex type using our theory. Proving completeness and soundness for all of these features and their synergies are part of our future work. Okay, now I'll go over how type checking actually works in our implementation in a bit more detail by walking through a simple example program. The example here is a constant function that returns 2. The return type here is clearly wrong. 2 is not a Boolean. And to type check this program, our first step is to transform the program to include concrete checks for the declared type. There is only one declared type here, but the same procedure can be extrapolated to programs with multiple declarations. The transformed version of the program is shown on the left. It's a little bit difficult to parse, so let's break it down. The highlighted boxes correspond to the key parts of type checking in the previous TC definition. Recall that to check function types, we need to generate an argument from the input type and then make sure the output is in the right type. In this case, we're generating a Boolean value argument and use type casing to verify if the application result is also a Boolean. Since 2 is the return value, it will not pass the type casing, returning an error. And now comes the second step of type checking in the implementation, using concolic execution to find any reachable error state. In this case, the goal of our concolic evaluator is this particular error clause, which signifies the presence of a type error. An example output is shown here. As you can see, our checker managed to spot the error in the declaration, correctly stating that the return type is an integer, which is different from the actual declaration. Okay. Here is a more complex example where we are implementing an insert function for AVL trees. The AVL tree type is highlighted in the yellow box, and it's a rather complicated refinement type on a recursively defined tree type. The error is over here in the red box. It's an incorrect rebalancing. So to detect this error, our tool essentially needs to be able to produce inputs that will lead to an AVL tree violating the declared type. Unfortunately, it is up to the task. It correctly identifies that the program implementation does not conform to the actual declared type. Speed and performance-wise, we compared our implementation with self-contra verification, more specifically with the artifact in the 2015 paper, Relatively Complete Counterexamples for Higher Order Programs, which focuses on finding counterexamples to racket contracts, which is actually very close to us in spirit. We ported most of their programs from their racket benchmark into our language, and the result is actually quite promising. Our tool outperforms their artifact in most cases. The blue is us, and the red is SCV. Note that this is a little different from the data presented in our paper because we have included some optimization post-submission. And as you can see, apart from a few cases, our tool outperforms theirs rather consistently. In the number of cases that our tool does trail behind a little bit, the gap is small enough that we believe they can be addressed by further optimization. Finally, let's talk about some limitations and directions of future work. An issue we're facing is correct types. By virtue of being co-RE, our checker will time out on correctly typed expressions involving recursion. This suggests that our checker will probably work better as an add-on to a traditional type system, which is able to handle most of the simpler type checking. We also would like to extend our theory to include more complex effects, such as states and exceptions. Finally, we want to further optimize our backend implementation. There are many optimizations yet to be applied to the concolic evaluator, and we believe our tool's performance will be further improved with these optimizations implemented. And that concludes my presentation. I'm ready to take any questions. Thank you.
We have time for a few questions. Can you step up to the microphone?
Do you think you'll give better error messages for these complex types using your add-on type checker?
Thank you. Yeah, error reporting is always a difficult problem, and we actually spend a substantial amount of time on trying to make the error message more intelligible. But yes, it is definitely a work in progress. Thank you for pointing it out.
So since we're at OOPSLA, maybe you can say a bit more about Is subtyping presenting any significant special challenges for your approach?
Actually, yes, because record subtyping presents a sort of asymmetry in the generator and the checker pair, because when we're checking for record subtyping, we allow much more inputs than, say, when we're generating something, because if we say a record of type A with field A and type int, when we check it, if we see something that's more specific with a B int, then we can say, well, you also pass because we only look for A. But that's a problem for generator because generator now have to be able to come up with everything with A field of type int, but also everything else in the universe that happen to contain an A label. So that is a really big challenge for us. And we had to kind of work in a lot of restrictions in the theory in order to accommodate that. More details to be found in the paper. Please go read the paper. But basically what we were doing to make that work in our system is to kind of put guardrails into our system to say if you kind of downcast your records to contain less information than it contains, you are kind of fixed in this state. After you are passed into a function that only takes in A int record, when you get out of it, you kind of just forget that you have a B field or a C field or whatever field you had before. That is just some sort of how we manage. I think it's kind of similar to how Java deals with it. Please correct me if I'm wrong, because I think we have some Java experts. My co-authors are in the audience. But that is not the ideal solution. We're trying to find a better solution to the problem. But yeah, subtyping is definitely a challenge.
Thanks very much. Okay, then the next talk is Seneca, taint-based call graph construction for Java object deserialization, presented by Joanna Santos.
All right, so good afternoon, everyone. Sorry for some minor technical difficulties in here. It is my pleasure today to present our work on call graph constructions for object deserialization. So to start with, call graphs are data structures that are very important for several interprocedural client analysis. And that means that if you have a call graph that is unsound, your client analysis will all be unsound as well. So one of the key challenges that we have when we are building call graphs, at least static analysis, is that certain dynamic programming features will make it challenging for us to infer what is the possible dispatch at a given call site. And in fact, there was a previous work that was published at ISTA in 2019 that investigated the soundness of different call graph algorithms with respect to certain programming features. One of these programming features was object deserialization. And as you can see here in the table that they reported in the paper, the deserialization was really not well supported by the existing techniques. So motivated by this fact, what we want to do is we want to build the call graphs that are sound with respect to this feature. But before I talk about my technique, let me take a step back and explain what exactly is object deserialization. So object deserialization is basically the process of you have an object in your memory, and you want to save this object. Somehow you have to convert this object that is in your memory into some sort of format. Could be a stream of bytes, could be JSON, could be XML. So this process is called serialization. Now, once you save that object and you want to actually use that object in your program, you have to convert it back from that stream of bytes back to the object in the memory. And that process of converting from this representation of an object back to an object in the memory is called deserialization. And object deserialization, serialization is available in multiple languages, such as Python, Ruby, PHP, Java. In fact, if you implement a machine learning algorithm, more likely you're saving your object, saving your model in a file. So that's exactly object serialization right there. So when it comes to Java, and not only Java, but several object serialization libraries, what we have is that developers, they are able to customize the process of serializing these objects. So for example, let's take a look of Java. When you're writing an object in Java, you're going to use the class called object output stream. When you use this class, what happens behind the hood is that, well, the object that you're saving at that stream of bytes, it's going to be serializable. So it has to implement the serializable interface. And if that object implements, the class of that object implement these callback methods right here called write object and write replace, these methods are invoked when that object is being saved. Similarly, when you are reading that object back from that stream of bytes back to the code, back to your program, if the data type of that object also implements certain callback methods, such as read replace, read object, these callback methods right here, they're also invoked during the deserialization process. So what happens is that existing call graph construction algorithms, they do not take into account these callback methods that arise at runtime, and because of that, these call graphs become unsound. So our goal in here is exactly to build a technique that can plug into existing call graph construction algorithms and can find these hidden methods, okay? These hidden edges. So how does our approach work? It works as follows. So this is a two-phase approach that relies on the taint states of objects to be able to compute a method dispatch. So how does it work specifically? So the first thing that we do is that we build an initial call graph that is supposed to be refined later. So at this initial phase, what we do is that we first take some things that is input, which is the program itself, a list of entry point methods, and what pointer analysis method you want to use, okay? So after we do this initial analysis is that we start from the entry point methods, and what we do is that we identify what places in our program are reading or saving objects, okay? So at these call sites, when we do, hey, read an object or save an object at this file, what we do is that we replace these invocations to syntactic methods. So the idea of the syntactic method is really to act as a placeholder of instructions to basically model how the serialization process will look like at runtime. So what we do is that at these serialization points and deserialization points, we create these syntactic methods. Now, at this initial call graph construction phase, these syntactic methods, they are empty. So they don't have instructions yet, but they need instructions, right? So what happens is that on the next phase, what we do is that we actually refine this call graph, these synthetic methods, to include instructions. So just as an example in here to clarify what is going to happen on this first phase, here at my left, I have an example of a Java code that is saving a list of students, an array of students, in a file. So as you can see here, when we build this initial call graph, we have a call graph that starts from the main method and has a few edges to the constructor of the classes being serialized. So for example, today's student class and the TA class as well. But as you can see here at the last call site, at line 11, when we do out.writeObject, noticing here that what I have is a node in my call graph, and that node is synthetic. That's why I'm highlighting that in yellow, okay? So what I'm going to do now on the next phase is get these synthetic methods in here and refine them, and add instructions to model how the deserialization process will look like. So now what I want to do next is, well, let's go ahead and refine these methods. So that's exactly the purpose of our second phase right here. So what we do is that we get this initial call graph, and we start expanding it. So how do we do this refinement? So the refinement happens through something called API modeling, which basically what we want to do in here is that let's try to model the behavior of this serialization API. So when we are modeling the serialization API, so that means when we are modeling the behavior of the program when it comes to saving objects, essentially what we do is that, well, we look at the type of that object. So we look at the points to sets of that object to be able to infer what is the object being saved. And what we do is that inside of our synthetic method called writeObject, what we do is that first we say, hey, we're going to downcast that object, we pass the subparameter in here to that data type. And then finally, we're going to invoke the callback methods in here, okay? So noticing here that if this object in here, the data type of that object, implements those custom callback methods, they are going to be invoked by our synthetic method. Similarly, an object can contain other objects in the fields. So if those fields are also serializable and they also implement callback methods, those callback methods are also invoked as well. So as you can see here on the next line, what we do is that we read the values of these attributes, and then we downcast them, and then we invoke any callbacks that they may have, okay? So this process happens for all fields for that object. Now, that was for to model writing an object, but how about reading an object? When it comes to reading an object, that process is slightly more complicated. And the reason is quite simple. When you read an object in Java, that object can be of any type. As long as you have classes in your program that implements the serializable interface, any of those classes, their instances can be read right here, okay? So at a given read object call site, any of those data types can be read back. So we have to be a little bit smarter when we are trying to model this behavior right here. So basically what we do is that, look, when you're reading an object in your program, we soundly assume that any classes that you have, any objects, will be any serializable class in your class path, including your application classes, library code, any of those data types are possible to be read right here, okay? And we also make a few assumptions. One assumption is that we don't assume that you're going to do dynamic loading. So only the classes that we observe at the class path are only the possible data types to be read. Another thing that we assume as well is that all of the fields in our objects are not null, so that we can infer that there are possible callbacks for these fields. And also, we look at the taint states of objects to be able to compute the method dispatch, all right? So let's take a closer look on how this algorithm looks like. So as I mentioned before, the taint states of objects will dictate how methods are going to be computed, how the dispatch will be computed. So if we are talking about taint analysis, the first thing we have to talk about is some common terminology in here, which is, so now every method in my program will have a context, and each variable has an associated pointer. And that pointer is basically for a variable under a given context. And each pointer now has also a taint state. And that taint state indicates whether that pointer is tainted or not. So now, what we want to do in here is that, well, let's look at those taint states when we are computing the method dispatch. So first thing we have to do is that we have to implement taint. We have to start flagging some objects in the program So in this case in here, the way we flagged these objects as tainted is that basically any object that that implements a callback method is tainted. So initialize those objects as tainted. So noticing here that on my synthetic method, I'm creating an object of type cache manager. That object will be flagged as tainted. Now, what we also do is that all of the fields of that object will also be initialized as tainted as well. Because if the object itself is tainted, all of its attributes are tainted as well. So this is how we initialize the taint states. Now, the other thing we have to do as well is that if the object is tainted, that means this pointer has also to be flagged as tainted. Okay? Now, the next thing that we have to do is we have to propagate states to variables in the program. And that propagation follows the semantics of Java. So when you have an assignment, that means that if the right-hand side pointer is tainted, that means that the left one should also be tainted. So essentially what we do is that we propagate the taint state from the right side to the left side. One thing I'd like to highlight in here is that the taint states are never removed. Okay? Now, when it comes to method calls, now we have going to take into account these taint states when we are computing the dispatch for these possible method calls. Okay? Now, the first thing that we have to do as well is we have to propagate the taint for those method calls. So essentially what we do is that we propagate the taint from the arguments to the parameters of the invoked methods. And then the other thing is that if that method is returning a value, the taint state of that return value should propagate to the value. Another thing that we do as well, which is in the case of instance methods, what we do is that we propagate this pointer as well. So if the receiver object is tainted, this pointer at the caller should also be flagged as tainted. So once we do that, now we can take into account those taint states when we are computing the dispatch for a given method call. So noticing here that at this example, I have x equals to an object O, and I'm invoking the method G and passing some arguments to it. So when I compute the dispatch, what I do is I take into account what is the data type of O, the static type of O, the context in which that object is, and the method signature. And what I do is that basically I look at what are all the possible serializable classes in my class path, then what are the classes that are actually accessible at that given context, because remember in Java some classes can be public, private protected, or package protected, so we also take that into account. And another thing that we also take into account, whether that class is type safe to the static type of O. So that means we compute the intersection of these three types in here, and the possible dispatch will be all the methods that match the signature of G that are from these classes in here, that is in that set. So once you do that, once we compute the dispatch, we add these methods back to the work list of methods because our algorithm to build call graphs is iterative. So it keeps analyzing these methods until there are no more methods to be analyzed on our work list. All right, so with that, we now evaluated whether our approach is actually sound or not. So we answered that by looking at two data sets. One is a data set of test cases by our previous work, and then another one is a data set derived from the And here what we look is that we look at how many test cases we passed and how many edges are in our static call graph that are not in the runtime call graph. So once we look at the soundness results, we can see that Seneca actually passed all the test cases for the first data set. And when we look at the performance of Seneca on the second data set, which is a data set of real Java programs, we can see that our approach actually overperformed the state-of-the-art. You can see here that our call graphs are more sound than the state-of-the-art approaches. Now, another thing we have to look at is the precision. Is our call graph decreasing the precision of the call graph? So what we look in here now is a different metric, which is how many nodes and edges are in the static call graph, but not in runtime. So when we look at this, we can see that actually our approach also overperforms a state-of-the-art approach. And this is also, we can also observe that when we look at the X corpus data set. And finally, another thing we looked as well is whether, now that we have this sound call graph, would this call graph be useful in a client analysis that is being used for vulnerability detection? So what we have done in here is that we built a client analysis that tries to find vulnerabilities caused by untrusted object deserialization. And what we have done is that we got 3 open source projects that have known deserialization vulnerabilities in them, and then we used our call graphs to see if we can find these vulnerable passes or not in the program. So as you can see here, when we compared our approach to a state-of-the-art approach called Salsa, we can see that our approach was able to find vulnerable passes in the program, including the vulnerable pass that was the one that had the actual vulnerability, but the state-of-the-art approach was not able to get any vulnerable pass, okay? So with that said, just to wrap up, we built an approach to improve the soundness of call graphs with respect to object deserialization. And compared to the state-of-the-art approach, our approach improves the call graph soundness without greatly decreasing the precision of these call graphs. And as you can see on the previous slide, this call graph was useful for a client analysis for vulnerability detection. With that said, I'm happy to take any questions that you may have. Thank you.
Any questions? Can you say something about how difficult is it to incorporate this approach in an existing call graph constructor like Duke or Walla or any of the others?
Excellent question. So this whole approach in here was actually built on top of Walla. So what we do is that, well, you select what is the pointer analysis algorithm you want, if you want 0, 1 CFA, NCFA. And then what we do is that we build this on top of it. So we modify the points to sets, and the taint states is also built on that. So it's not straightforward, but it was already built on top of Walla. So all the data structures that we are using is on top of Walla. So if you build an algorithm on top of Walla, our approach will work as well. So it would integrate just fine.
And is it something that is easily localized in a single component, or is it that you have to make changes all over the place to incorporate this technique?
We did not have to make any changes at the Walla side, so it's really localized. Okay. Yeah, it's modular. No,
please step up to the microphone.
So I enjoy your talk, and I have one question that I'm curious about. So you mentioned modeling the behavior of the serialization API. You talked about the cases for reading and writing an object. And I'm wondering whether, because all of these are approximations of actual runtime behavior, I'm wondering whether, you have an idea of any failure modes that you've encountered following such a model?
So are you asking about limitations of the modeling part?
Yes, or any directions for future work that you have in mind.
Excellent question. So some of the key challenges in here comes with collections. So the way we assumed is that when you have a collection, we just assume that we look at the static type of the collection, and then we assume that, well, that collection can have at least one. That means that there are several edges in there that will not arise at runtime. It is possible not arise at runtime likely, right? So it makes it more imprecise, but it sounds can arise at runtime. There could be a program that has those edges. So a possible future that we could tune this down a little bit so that it's not as imprecise. Yeah.
I see. Thank you.
Yeah, thank you.
Let's thank Joanna one more time. Okay, then last but not least, VerySQL, bounded equivalence verification for complex SQL queries with integrity constraints. presented by Pinhan Zhao.
Hello everyone, I'm Pinhan, and today I'm going to present our work, VeriEco, bounded equivalence verification for complex SQL queries with interior constraint. This is a joint work with Yang He, Xinyu Wang, and Yuepeng Wang from Simon Fraser University and the University of Michigan. Let's begin by discussing why the task of checking equivalence for SQL query is important in today's data-driven world. So database management systems and frameworks like MySQL and Calcite often rely on rewriting to optimize a slow query to a faster one. And we want to ensure that the rewritten query is semantically equivalent to the original one with formal guarantees. And in case of non-equivalence, we want to provide a counterexample to help the developer fix the incorrect rewrite. And checking equivalence is also useful for automated grading, such as LeetCode. And in this case, we want to automatically verify if a user solution is correct against a ground truth query and provide a counterexample as feedback to the user to illustrate why the query is wrong, if it is wrong. So let's consider a simple example. In this example, I will illustrate how a query that solves a real-world problem looks like. Suppose we have a database with two tables. We have table customers, which contains customers' information, and we also have an orders table, which tracks which customer has bought which product. And there are also interior constraints associated with the schema. Specifically, customer ID is a prime key of the customers table, and order ID is a prime key of the orders table, which means that these attributes must have a unique and non-empty values. And the customer ID is a foreign key of the orders table, which restricts that each customer that bought a product must associate with an existing record in the customers table. And given this database, we are asked to write a query to find the customers who bought both product A and B but did not buy the product C before. So in this case, a desired output will be like this. Specifically, there's one row in the output table that the customer ID is 1 and customer name is Alice, who is the only customer who bought both A and B but did not buy the product C. And here we have a query that a developer may write to solve this task. It's fairly complex, so let me walk you through it in the next couple slides. Intuitively, the query uses a select from where structure to retrieve all records from the customers table that satisfy the given predicate. And in this case, we want to know each customer has bought product A, B, and C before. And to achieve this, we need to write 3 subqueries. The first subquery identifies all customers who bought product A before. And we use an in expressions to check if each customer is in the subset of those who bought A. And similarly, the second query identifies those who bought product B before. And the third query ensures that we exclude any customer who bought product C. And finally, the query returns all records that satisfy the conditions. As we can see, the query is fairly complex. But in the real world, a user may write even more complex queries. And it is often very challenging to verify a pair of 2 queries like this. So in this work, we aim to solve the problems of checking equivalence of real-world SQL queries. And to do this, we conduct a thorough study of over 24,000 query pairs. So let's see how these queries look like. Firstly, real-world queries often use different kinds of interior constraints, like primary key, foreign key, not null, and many others. There are more than 95% of queries in our benchmark require consideration of interior constraint. And there are more than 73 benchmarks uses the aggregate functions, like average, max, and mean. And there are 66% of queries use group by. These features are very important when writing the analytical queries. And there are also more than 20% of the queries use the order by operation, which is necessary to sort the query result. And the challenges that make the task of checking equivalence difficult can be broken down into 3 key issues. Firstly, prior work are very limited in handling an expressive set of SQL queries. Existing approaches like HowSQL and UDP convert SQL queries into an algebraic structures. However, this intermediate representation often lacks in expressiveness needed to accommodate an complex SQL syntax. Secondly, it is important to account for rich interior constraints commonly used in real-world queries. And the third important feature to support is list semantics. Specifically, list semantics treat tables as lists and preserve the ordering of tuples. This is necessary to support the order by operation. However, prior work does not support list semantics and therefore cannot handle queries that involve an order by operation. Due to these limitations, prior work collectively support less than 2% of our benchmarks. So we want to address these challenges. To bridge the gap, firstly, we formalize the semantics for a large subset of SQL, reflecting the rich features used in real-world queries. Building upon this foundation, we develop a verification approach, VeriEco, that is very standard but meets 3 key criteria. It supports an expressive SQL syntax to handle complex SQL queries. It supports rich entirety constraint, and it supports checking equivalence under list semantics to account for ordered results. This approach would allow us to tackle the full spectrum of SQL equivalence verification challenges identified in our benchmarks. And in the rest of my talk, I'm going to expand on our formal semantics and our verification approach, VeriEco. So our formalization covers a rich subset of SQL operators, reflecting the rich features used in real-world queries. For example, we support the fundamental select, project, and join operators, as well as the group by and order by. We can also handle complex expressions like aggregate functions and case expressions. Like standard SQL, we also model our SQL semantics use 3-value logic. Specifically, a special non-value may be used to denote an unknown information. And to switch between the bag and list semantics, we denote our semantics in functional programs with higher order combinators that operate over lists. We interpret tables using lists when necessary to support the order by operation, which requires preserving the ordering of tuples. And we treat the table as bags when the queries don't involve an order by operation. So now let me introduce our approach, VeriEco, to solve the equivalence checking problem. VeriEco takes a pair of 2 queries as input along with a schema and a set of interior constraints. And then we will build a symbolic database. Here, a symbolic database is a finite input space that considers all possible input tables with number of rows up to a certain size. But the value of the cells are unbounded. And then VeriEco will symbolically execute 2 queries on the symbolic database and produce their symbolic outputs respectively. And we'll then ask an SMT solver to determine, given the symbolic database, whether it's possible that 2 queries will produce the different outputs. And if this condition is unsatisfiable, then 2 queries are bounded equivalent, which means that 2 queries will always produce the same output on all possible input tables up to a certain size. And if the condition is satisfiable, then we found a counterexample that can make 2 queries produce different outputs. Now, let's walk through a simple running example to illustrate how VariEco works. Consider this simple schema with an employee table with 2 columns, ID and age. And there is also an entire constraint that the ID column is a primary key, which means the value of the ID must be unique and cannot be empty. And let's look at the 2 queries we want to compare. Query 1 selects the ID from the employee table where the age is strictly greater than 30. And query 2, on the other hand, selects the ID from the table where age is greater than or equal to 30. The queries look very similar, but are semantically non-equivalent and can produce different outputs. And VariEco will begin by encoding the entire constraint. And in this case, we want to encode a primary constraint on the ID column. To represent this, we'll first create a symbolic database. And for our example, let's consider a bound of 2, which means we'll consider all possible input tables with up to 2 rows. And the entire constraint is encoded as a formula phi c, which restricts that the value of the ID column cannot be null and are distinct from each other. This encoding makes sure that VariEco will consider and reason about all valid database instances that conform to the given entire constraint. And then VariEco will encode 2 queries executing on the symbolic database. And we'll first create a symbolic table R1 to represent the output of query Q1 with 2 fresh symbolic tuples. And then we'll create a formula phi1 to encode the query Q1. And our idea is to use an unitary function called deleted to denote whether a symbolic tuple exists or not in the table. And then we'll first encode the where clause. Intuitively, if a tuple has age greater than 30, then the tuple is preserved in the output table. And then we project the ID column by copying the values. Otherwise, if the tuple has age less than or equal to 30, then the tuple is deleted in the output table. Similarly, we can create a formula phi2 to encode the query Q2. And finally, we'll construct an equivalence condition phi eq that states the outputs of 2 queries should have the same size and contain the same tuples with the same multiplicities, which basically means that the 2 queries are semantics equivalent under the back semantics. And more specifically, it means 2 multisets should contain the exactly same elements. And with all the pieces in place, we can now check for equivalence by solving this formula above. And in this case, VariEco will find a counterexample that can make 2 queries produce different outputs. Specifically, there's 1 row in the table where age is exactly 30. This row will be included in the output of query 2, but not query 1. We evaluate VariEco. To evaluate VariEco on solving real-world tasks, we use 3 different benchmark suites. The first and largest is from LeetCode with 23994 query pairs. And each benchmark is a pair of 2 queries of a user submit query and a ground truth query. And the second benchmark is Apache Calcite with 397 benchmarks. And each benchmark is a test case that a slow query is rewrite to a faster one via rules. And we also take another 64 benchmarks from prior literature. And we compare VariEco against several existing approaches. We included bounded verifiers like COSAT and QEX. And we also compare VariEco against full-fledged verifiers like SPLASH and HouseEco. Additionally, we included testing approaches, Xdata, and data filler. So the evaluation results show several key points about VariEco's performance. Firstly, it supports over 75% of our benchmarks, significantly better than all other tools we compare it to. Also, VeriEco is very good at identifying non-equivalent query pairs. And the counterexamples identified by VeriEco help us find serious bugs and contributed to real-world systems. Firstly, VeriEco identified 4 non-equivalent rewrite rules in Apache Calcite, which rewrite a query to a semantically different one. We reported these issues to Calcite maintainers who confirmed these issues. This shows that even in a well-maintained and extensively tested system like Calcite, VeriEco is able to uncover very tricky bugs that escaped existing testing processes. And VeriEco also identified a serious MySQL bug. During our evaluation, we found 2 counterexamples produce the same output when executed on MySQL, which are supposed to produce different outputs. So we manually inspected the counterexample and the queries and found it is because the execution result of MySQL is incorrect. So we reported this issue to MySQL team, who confirmed and classified this issue with serious severity. Additionally, VeriEco also identified more than 3,500 counterexamples for LeetCode benchmarks, which suggests that many user-submitted queries that are accepted by LeetCode may be actually incorrect. We filled missing test cases report for several problems and provide the counterexamples identified by VeriEco, which then help LeetCode augment their existing text suites. And VeriEco is also open source, so please definitely check it out. And this is the end of my talk. Thank you for your attention.
We have time for a few questions. Please step up to the microphone.
So thank you for your talk. I enjoyed it a lot. I think one of the major aspects to your work is that you formalize the semantics via, SMT encoding for a large subset of SQL. And I guess that, this may have, more use cases beyond, verifying that 2 queries are equivalent. So have you considered any directions for future work?
Yeah, that's an extremely good question. So actually, we are working on another project that applies this encoding to solve more problems in different domains. Yeah, that's our future work, indeed.
Yes, so looking forward to that, and thank you.
Thank you so much.
I was sort of thinking along the same lines. So maybe wouldn't another interesting case perhaps be a situation where one query produces strictly fewer results than another query? Would that potentially be of interest in some cases?
You mean like enforce a query's result must be?
So inclusion of a set of results in another set of results.
Yeah, that could be a potential application of this. Yeah, and I think our encoding should be applicable to this application.
Time for one more question. So if I understood correctly, you are bounding the tables when you're looking for potential counterexamples. In the all the properties that all of the equivalences you were able to disprove, is there a sort of minimum depth or max or general intuition that you got about how large your counterexamples generally will need to be?
So I believe the small scope hypothesis is applicable to our domain. So many counterexamples identified by VeriEco is indeed very small, like 2 or 3 rows in the table. And there is a statistic in our paper, and we can catch on this offline.
Got it. Thank you.
Okay, let's thank Pinhan again. And that concludes our session and today. Thank you.